The following message is best viewed on an oscilloscope.
So now it's sorry?
Share that slide, okay?
So maybe I think I want to say something as the session here. So yes, so thanks. Welcome everyone to the today's session in the BSM. So okay, so today's topic is on the prospects from the future experiments, as well as the latest sushi search results in the Atlas and CMS, together with the analysis technical developments. So today's chair me, so Yu Nakahama from Nagoya University, and Alex from University of Cincinnati. So yeah, so each speaker has the 15 minutes for in total. So 12 for a talk, followed by the 3 minutes discussion. So I'll remind you when 2 minutes are left in your talk. So basically after 10 minutes. Yeah. Okay, so now we have 14 people. So since we have the full agenda, so we can just get started. So Seo, could you start the shared screen?
Okay.
So our first speaker is Shun Seo from the University of Tokyo, who will be presenting the precise spectroscopy of myonim hyperfine structure at the JPark. So please go ahead.
Okay, can you see my slides?
Yes, perfect.
Okay, thank you. Hello, I'm Shun Seo. I'm very pleased to have this opportunity today. And in this presentation, I'd like to talk about precision measurement of myonim hyperfine splitting we have been performing in Japan. So first, standard model of physics is best theory we have. But there are still many problems such as neutron mass, mu G-2, and so on. So we have to search for physics beyond the standard model. And for the test, we have 2 approaches mainly. One is direct approach by production of new particles using high energy experiments, such as Atlas experiment at LHC. And the other is indirect approach by high precision measurements. And comparing, in this approach, comparing some values very precisely, then it leads the BSM. And we, museum group, has been taking the latter, this precision measurement for BSM. So a museum group have been performing precision spectroscopy of myonim hyperfine structure. Myonim is the bound state of a positive muon and one electron, like this figure. And there are 2 independent methods for the measurement. Please see this figure. And this shows a bright line diagram of myonim in one state. And the horizontal axis represents magnetic field, and the vertical axis, the energy. And One of the methods is to measure the HFS at zero field trajectory, and the other is the measurement at 1.7 Tesla, measuring two frequencies, nu 1, 2, and nu 3, 4, and using these relations, we obtain two values, delta nu and magnetic moment ratio of muon to proton. And the world record of the measurement was obtained at Los Alamos. And our goal is tenfold improvement by using the world's highest intensity pulse muon beam at ICHEP in Japan. Then we have been planning to obtain 200 times more statistics. And in this slide, I'd like to talk about the physics motivation of our measurement. There are two motivations, and one is the validation for the bound state QED. Through the precise measurement, we can compare the value between experiment and theory, and that leads to the QED validation, and also to search for new particles, test of Lorentz invariance, and so on. Oh, sorry. And the other is the contribution to muon G-2 experiment. And we measure magnetic moment ratio, and this is an essential parameter to the muon G-2 experiment. See this figure, yellow band shows theoretical value of muon G-2, and blue shows the experiment one. And there are 3.7 sigma discrepancy. So new muon G-2 measurements have been planned at Fermilab and JPAC. And our group measured the mu HFS, and it contributes to the mu HFS uncertainty contributes the 30 ppb out of 540 ppb. So our measurement is also meaningful to the experiment. So in this slide, I'd like to talk about our experimental procedure. Muon beam polarized to upstream is injected to the microwave cavity. And the cavity is placed in a gas chamber, and these are filled with krypton gas. And these are surrounded by magnetic shield or superconducting magnet. And then the injected muon stops in cavity and captures an electron from krypton atom, then forms a muonium atom. And if we input the microwave of the mu HFS frequency, then the muon spin flips to the opposite direction. And after 2.2 microseconds, through this muon decay, positron emits. And the positron goes preferentially to the direction of the muon spin. So after inputting the microwave, the muon and the muon decay, positron emits to the downstream mainly. And without the microwave, the positron goes to the upstream mainly. So by counting the number of positron at downstream and taking the ratio of positron times spectrum between RF on and off, then we can determine the mu HFS. And in the measurements, there are two dominant systematics. One is pressure shift of the hyperfine structure due to atomic collisions between muonium atom and krypton atoms. So we need to measure it at various pressure like 1.0 atom and 0.3, and then extrapolate in vacuum, and then we can determine the value. And this extrapolation causes uncertainty arising from the gas pressure. So in order to suppress the uncertainty, lower pressure is preferable. And the other dominant systematics is magnetic field for high field experiment. And we need less than 1 ppm homogeneity in the muon formation volume. In this figure, here's the muon beam, and here's the microwave cavity. And in this volume, we need the homogeneity. And its size is like a rugby ball. And also, we need precise magnetic probe. And our goal is 1 ppb precision. So here is the roadmap of our experiment. Since 2011, we have projected it from here. And zero field measurement is ongoing for demonstration at existing beam time. And we have several beam times in 2016 to 2019. And for the high field experiment, a dedicated beam line is under construction. But we have been preparing for it, such as the R&D of a magnetic probe, and also the achieving the good homogeneity of the magnetic field. And in this slide, I'd like to talk about the beam times from first to third. In the first beam time in 2016, we observed the new HFS resonance successfully with first beam at zero field for the first time in the world. And in the first beam time, SN ratio was limited due to a small microwave cavity, and also we used one atom krypton gas because it was necessary to stop muons in the cavity. So in the second and third beam time in 2017 and 18, we made a larger cavity, and then it enabled us to use lower gas pressure and 1.0 atom. But even at low pressure of 0.3 atom, the systematic uncertainty due to a pressure shift remained. So in the latest beam time in 2019, we used krypton helium mixing gas because it might cancel out the pressure shift, and so we expected to suppress the systematic uncertainty, to use the mixing gas is the best. And in this beam time, we used various pressures and the krypton mixing rates. And this figure shows the relation of the krypton mixing rate and the transition frequencies at the mountain. And from this figure, we found an optimum mixing rate as the 30% here. And then systematics due to gas pressure will be less than 1 ppb. In 2018, the systematics was 35 hertz, and it will be a few hertz. So the improvement will be enough for us. And also, in this beam time, we achieved a world record in the field measurement. As a preliminary result, we achieved 150 ppb statistical precision, and the world record for zero field is 300 ppb. So we have the twice statistics. So, and in the final slide, I'd like to talk about the presentation, preparation for high field experiment. Here is the new dedicated beam line, and it is still under construction, and we expect the first beam will be in 2021. And as the preparation for the experiment, we have been achieving the high homogeneity of magnetic field. In the result of the shimming in 1.7 Tesla, we achieved 0.0 ppm. And furthermore, in the recent result in 1.2 Tesla, we achieved 0.1 ppm. And the homogeneity is enough for our experiment. And in addition, we have developing the precise magnetic probes. And its accuracy is now about 10 ppb. And also, we have been cross-calibration. We have been performing cross-calibration with muon G-2 group at Fermi Lab, and then developing the probe furthermore. This is the picture of the standard probe. So here is a summary. We have been performing muonium hyperfine spectroscopy as search for BSM, especially to the QED validation and the G-2, muon G-2 measurement. And we have successfully have been measuring it. And our goal is the mu HFs with 1 ppb precision, and the magnetic moment ratio of muon to proton with 10 pp precision, and performed at the field successfully, and preparation is also in progress. Thank you.
Thank you so much for this very nice talk. So are there any questions or comments to this talk?
Actually, can I have a question? I'm Michal.
Sure, sure.
I just didn't quite understand. I mean, why krypton is your primary choice for this noble gas filling of
why we use krypton? Your question is that for muonium formation, and also why we use krypton is this slide shows why use krypton gas. Some methods for production method is here, and the target is preferable for our measurement because the production rate and polarization are sufficient, and also the comparison of the gas target this table shows, and due to the energy, the krypton is the one of best target for the muonium formation.
Okay, thank you.
Yes.
Okay, thank you so much. So I think now we move on to the next talk. So thanks, Seo. So yeah, so next speaker is Maria Teresa. So maybe could you start the shared screen first?
Yes.
Okay, so our next speaker is Maria Teresa Pardo Dubella, who will be talking about the ILC as a SUJI discovery and precision instrument. So please go ahead.
Can you see my screen?
Yes, perfect.
So it's already, wait.
Sorry, now I see just on the top left, but it's only for me, or? Maybe
Can you see it?
I can
also see only the left, upper left.
Yes, yeah, exactly. So maybe could you just retry?
Try again. Okay.
Yeah.
So new share. Share. Now you see it.
No, actually no. So maybe you can just. I think you chose the different screen on the sharing. So.
Stop sharing and I try again, one again.
Yeah. And then maybe you don't need to do the full screen. Yeah.
So
Because
set
it may
application
maybe,
window.
yes.
Yeah, now I did it.
Yes. Thank you. Perfect.
It's okay now?
Yes. Yeah. I think you don't need to do the full screen. Yeah, because by doing the full screen, then the something strange is happening. So.
Okay, so now you can see it.
No. Maybe you can stop. You should stop the full screen, and then
So
yes.
now you can see it.
Yes, that's good. Thank you. So
Okay,
please
so
go
now I
ahead.
make it like this. Okay, so well, I'm going to present this talk on behalf of the ILD concept group, and it's mainly a brief presentation of these two works where we want to show the capability of the ILC for discovering or respectively excluding SUSI, and also for measuring once that SUSI is discovered, the SUSI observables with such a precision that we could make important predictions about not only SUSI breaking, but also some fundamental particle physics. So now, you see the next one now.
Yes, we
well,
can. Yeah.
Okay, so now we know that supersymmetry could be the solution, or at least give some light into current problems of the standard model, but up to now there is no evidence of SUSI at the LHC. They could establish some limits for exclusion and discovery, but they are really strongly model dependent. And also there are some scenarios that would be very important for explaining the problems of the standard model, but they cannot be, or they can be with much more difficult study at the LHC experiments. So the complementary nature of the physics in the electron-positron colliders offers also interesting scenarios where we can discover SUSI. And we can cover these scenarios that would be very challenging for the LHC. Also, the conditions of our experiments and accelerators allows us to compute exclusion and discovery limits in a model independent way. So here I show the exclusion limits for charging of production at the discovery and exclusion at the atlas, and I pointed out 3 points that are the ones that we will focus this study. And this is motivated. The next one, no. And this is motivated because of the electroweak naturalness, and this requires 4 light Higgs xenons with masses about 100 and 300 GeV. The lightest the best, and in a very compressed spectrum. So the observation of these Higgs xenons for the LHC would be very challenging, but not for the ILC, where we have an electron-positron collider with the capability of upgrading the energy with a very high polarized electron and positron beam, very well-defined initial state, clean and reconstructible final state, hermetic detectors, and without a trigger. So I will, due to this theoretical motivation, I will also show the capability of the ILC for finding SUSI in the Chargino channel. So the Chargino is a mix between the superpartners of the Higgs and the Ws. So I will first show that, and once that we know that we could see the Charginos in any scenario, I will go to the Higgs xenons for studying some properties. So, well, for showing that we are able to see the Charginos in any scenario, we will go to the worst case. For that, what we have done is compute the Chargino production cross-section in a very wide range of parameters of the SUSI space, and we only assume the minimal supersymmetric standard model and the air parity conservation. And this could also be considered the worst scenario. So there we compute which are the lowest production cross-sections, and this lowest production cross-section will be compared with limits extrapolated from LEP. And this is also the worst case because we have not taken into account any improvement in accelerator or detector technologies. So depending on the composition of the Charginos, we have divided the study in these 3 scenarios: Higgs xenon-like, Vino-like, and a mixed Charginos. And also because the production is not only due to the S channel, but also to the T channel with exchange of S neutrinos. For these of the scenarios, we have compute cross-section for high and low values of the S neutrino masses. So now I show here the worst values of the cross-section. So in the case of high fermions masses, the low value is reached for the Higgsino-like case. But if we decrease the masses of these neutrinos, we see that there is destructive interference between the T channel and the S channel. This destructive interference affects only the Vino case because of the low Yukawa couplings for the neutrinos. So in this case, the lowest values of the cross-sections are reached when the neutrino masses are close to the kinematic limit. This is also important because upgrading the energy, we could change this lowest value. The studies were done only in this polarization with electrons left polarized and the positrons right polarized because the contribution of the inverse polarization is practically negligible. So the values of these lowest values of the cross sections were compared to limits extrapolated from LEP, and we have only taken into account the relation between the cross section limits and the luminosity. No any improvement from our side, and so with this comparison, we could obtain the mass limits for Chargino exclusion and discovery, and this is what I saw here. So I saw the mass limits as a function of the Chargino mass and the mass difference between the Chargino and the neutralino. So the light blue are the results from LEP. Then we have our results, and I have also plot the dark color there are limits from Atlas, but they are really model dependent, and as we see, they don't cover the full space of the full kinematic space. So what we can see is that with our limits for high fermions masses with mass differences more than 3 GeV, we can go practically to the kinematic limit, and the difference between exclusion and discovery is only a few hundred MeVs. So we will go now to the region with the mass difference between the mass of the pion and 3 GeV. Here there is a drop in the efficiency from LEP because they were not able to see the soft decay products of the Chargino decays. So they had to ask for an initial radiation photon in the trigger, and this will decrease the efficiency. But of course, we will not have trigger in the ILC. We want in any case to take this and compare it, and we see that in any case we go close to the kinematic limit, only a few GeV apart, and exclusion and discovery are only 5 GeV apart. And then if we go for the mass differences below the mass of the pion, the Chargino can be seen as a charged particle flying through the detector, and this we are really at the kinematic limit. So even in the worst case, where the fermions masses are close to the kinematic limit, we are able to see the Charginos up to 200. The discovery limit goes up to 243 GeV for the region with more than 3 GeV mass difference. And even in the worst case, we have exclusion limit up to 225 GeV and discovery up to 205. For mass differences below the mass of the pion, we are always again in the kinematic limit. So as conclusion of this part, I want to say that we have not taken into account in improvement of the ILC, like polarization, non-trigger, and also the small bin size. We have also not added any loop corrections in the cross-section, and this will increase the Chargino per production. And also that we wanted to compare the case with lowest fermions masses, but this case were not treated at the LEP, and also this could imply new topologies because probably if the S neutrino has a low masses, also this electron will be there, and it could be that this will be the lowest, the next to lightest supersymmetry particle and the first in being discovered. But in any case, we want to add this for completeness. So I go now to the second part of the talk. So here we want to see that now.
Sorry to interrupt, but I think you have just three more minutes. So.
Okay, I go fast. So, I mean, we have seen the Higgsino. Now we want to see that we can measure observables there. So we will work with 3 scenarios. The important point are that 2 of them have a good unification of the Gauchino mass, and the third one not. We have studied 2 channels, and from the kinematical distribution of these channels, we have computed the masses of the 4 Higgs and also the cross section. And with these values, we could extrapolate it. We use also the Higgs mass and the Higgs decay branching regions taken from another ILC studies, and we could make some predictions in the good scale, weak scale, and also the testing the mass unification. So in the good scale, what is important is that we have fit this to the model underlying our first benchmarks. This has the SUSY breaking scheme is, I mean, we have a Gaussian mass unification at the good scale, and we see that if fitted to the correct, the right model, we cannot exclude any of our benchmarks. Even if the third one was not underlying this model, we cannot exclude it because we have chosen the masses to be very close. But if we take any other two models, then yes, only with 0.1% of our luminosity, we could discard them. So we are really very sensitive to the breaking scheme, and we could distinguish this with our observables. We have also fit the parameters to the width scale. For this case, these are phenomenological models where playing with different parameters, we see if that even taking parameters entering the Higgsino sector at a loop level and at a tree level, we are able to predict with very high precision the masses of heaviest Higgsinos and also of the Higgs, but we are also able to make to put limits to the masses of the colored fermions, and this is very important because this could be important input for the hadron colliders like the LHC. So even if we work now with a model with only 4 parameters entering at tree level, we see that we can really increase the precision. And this is also very important because this could also improve the rest of our studies. And the last point is to test the unification. And here we have evolved the fit of our weak scale parameters to higher energy. And we can see that we get a good Gaussian mass unification at the good scale. And we can also go the other way around, assume our underlying model and make a prediction of the gluino mass. And this could also be very important for the LHC. And the last point is in the model that where we have taken without, in the scenario without a Gaussian mass unification, we see that if we evolve the values, we cannot see this unification. So with not so much precision, because this model had a very small mass difference, we are able to see that there is no Gaussian mass unification, and this is also a very important point. We can also go further, improve the precision, taking the measurement for the weak model with only 4 parameters. What I said that is increasing the precision. Take also a measurement of the gluino mass from the LHC, and here we go still, we can even predict the energy for the Gaussian mass unification, and this is really the value that we had in our model. So we can see that even with the worst case, worst precision, we can see that we don't have unification, and if we improve the precision of our measurements, we can include even predict what the precision, the unification will be. And only for conclude, I want to say that in this talk we only wanted to remark the possibility of the ILC for measuring, for discovering SUSY or for measuring with high precision the observables, but we also wanted to show how important is the interplay between the different accelerators. So how the results of the electron-positrons accelerators could help the LHC, and also how the predicts the results from the hadronic colliders could help in the improvement of the studies at the ILC. We have also made some studies about dark matter that for lack of time, I could not show here, but there it was also very important the interplay between the ILC results and experiments dedicated to the detection of the WIMPs particles. I also want to show that, well, today at 4 European time, we will have a Zoom room. Here is the link where we can discuss about the different talks of the ILC. So.
Thanks a lot for this very comprehensive talk. So maybe are there any questions?
Yes, good morning. I have a question from my side, which is maybe it's not so relevant to the talk, but it's more general. Maria, can you tell us a few things about the ILC status now as an accelerator?
So now, I mean, there are some talks also about, I mean, there was some talks about that, but I mean, now is it the good way is the European groups, the United States and also Japan, they agree for going further with the project. So, I mean, yeah, it's the light, the red light is there for continuing the project.
Okay,
so
thank you. That's encouraging. Yeah. Thank you so much. Thank you.
Okay, so are there some urgent questions? If there are, if not, so we move on to the next talk. Thanks a lot, and then maybe further discussions can continue. Yeah, on a matter most or also the dedicated session. So, yes. So now our Philip, maybe could you start sharing your slide?
Yes. Good morning. Can you see?
Yes. So maybe yes. Our next speaker is Philip Roloff. Who will be talking about the quick potential from new physics. So please go ahead.
Okay, thank you very much. So I'm going to talk about the studies of the new physics potential of a mighty-TeV plus/minus machine like CLIC, which we have done in the last couple of years. So just as a reminder, of course, CLIC is a linear collider similar to the one which we have seen in the previous talk. However, it's based on the two-beam acceleration scheme where we operate the cavities at room temperature. This gives gradients of 100 megavolts per meter and allows us to build a machine of up to 3 TeV in a manageable size. We also have electron beam polarization of 80%, which of course is relevant for some of the studies which I'm going to show in the following. So you wouldn't really start with the 3 TeV stage from the beginning, but you would construct such a machine in several stages. Here you see the baseline scenario, which is assumed in this presentation. So you would have a first stage at 380 GeV, targeted also at Higgs and top precision measurements, and then high energy stages, which here are assumed at 1.5 and 3 TeV. And you see in the plot on the right how such a program of 27 years could look like. And you also see that we collect more integrated luminosity once we go to higher energies, which is really a feature of linear colliders. Of course, this is speculative and could, of course, be adapted to possible discoveries at the high luminosity LHC or at earlier CLIC stages. On page 4, you just see a plot of the cross-sections for various important standard model processes in the plus/minus collisions as a function of the center of mass energy. And of course, there's a wide range of processes which we can study. So of course, it starts with 2 fermion production. And then if we go a bit higher, we have WW production. And then if we cross the threshold for ZH production, we reach the region which people at the moment discuss as a Higgs factory. If we go even higher, we start producing top quark pairs. And then if we even go higher, we have the production of 2 Higgs bosons, either in double Higgs Strahlung or at the highest energies in WW fusion. And of course, this is complemented by a program for direct searches for new physics, which in many cases benefit from the highest possible energies. But what you see in this plot also is that actually to exploit the full physics potential of such a machine, you really want to measure at more than 1 energy stage. So, of course, we can start by looking at some of these precision processes which you have on the previous slide and see what kind of information in various new physics scenarios we can extract from them. As a first step, what you see on this slide is basically an EFT fit. So you see the precision on various dimension 6 operators, where as input to the fit, projections on Higgs couplings, on top quark observables, on WW production and then fermion production are used. And you basically see how things evolve when you start from the first CLIC stage in red to the combination of the first and second stage, and then finally in green when you combine all these 3 stages. So you see we can reach improvements with respect to high luminosity LHC in the range of 1 or 2 orders of magnitude, really depending on which of these operators you look at. But to make this a bit more concrete, of course, we can translate these limits in various new physics models. So let's start with compositeness. And what you see here is basically the expected reach of click for the composite Higgs and composite top scenario, where you basically see by different colors the limits which are provided by various processes. So for example, in the composite Higgs case, from Higgs production and from 2 fermion production. And then for the top case, you see what can be obtained from TD bar production or from TD Higgs production. What you see in these plots is basically on the x-axis the compositeness scale, and on the y-axis the coupling strength of the composite sector. And in both cases, we basically reach about 10 TeV in the compositeness scale. And then if you have a favorable choice of the coupling, this can even go much higher. So after this, we can also look at another very simple case, which is, of course, Z prime models. What you see here is basically a plot from the European strategy for a neutral gauge boson Z prime with a mass m that couples to the standard model particles equal to the hypercharge. And basically, you can translate one of these EFT operators into the coupling, as you see on the slide. What you can see is basically the reach in the mass versus coupling plane. And of course, if you are at very low masses, of course, hadron colliders will provide some direct reach. But of course, if you go to very high masses, then you have indirect reach from precision measurements, where you can reach very high mass scales for a click collider, for example, of 3 TeV, as you can see on the slide. Just as a side remark, the slide ends at a coupling of 1.5, which basically corresponds to a width of the resonance of 30% of the mass. One more example. So if we would look at the process E plus E minus 2 fermion pairs at high energies, we can also look for dark matter candidate contributions in loops to this process. And basically what you see here is the expected precision or the expected reach for various electroweak multiplet states with hypercharge Y. And you see that in case of the Dirac fermion triplet candidate, so this is the one where I have put this green circle, we can basically reach the thermal dark matter mass, which is very encouraging, of course. So let's move from these examples of indirect sensitivity to direct searches. Of course, in the plus E minus machine is really suited to study precisely couplings and masses of particles that couple to photons or Z bosons or Ws. And then the sensitivity often extends up to the kinematic limit. So for example, half the center of mass energy for pair production. We typically can reach very rare processes due to the absence of QCD backgrounds. So this makes click especially suitable for electroweak states. And then polarization of the beam and threshold scans can be useful to constrain the underlying theory. So just a couple of examples. So let's start with something very simple. However, this is being discussed quite a bit at the moment, which is of course a heavy Higgs. So a heavy scalar mixing with the Higgs boson. And what you see here is basically the plane of the mass of the heavy scalar versus the mixing angle with the standard model Higgs boson. And what you see in the blue and green curves is the direct reach of click in production of the heavy scalar in vector boson fusion and in decay to 2 standard model Higgs bosons. You see also in the dashed line the reach indirectly from the precision measurement of the Higgs couplings, and you basically see that direct and indirect for this case are complementary, because depending on the value of the mass of the heavy scalar, different approaches give you the best sensitivity. Moving on to another interesting case, which are doubly-charged Higgs bosons in type 2 seesaw models. So as indicated before, one nice feature of E plus E minus is that basically the pair production cross-section is almost flat up to the kinematic limit, which you see in the plot on the top right. So here we compare the production in E plus E minus with the production in proton-proton collisions for two different center of mass energies. Then, of course, how the doubly charged Higgs boson decays really depends on the triplet vacuum expectation value, as you can see in the bottom right plot. We have chosen here a benchmark point of 10 to the minus 2 GeV, where the doubly charged Higgs basically decays exclusively in W pairs, which is also quite useful because here the constraints from the LHC are very weak. And what you see is basically the required luminosity for 5 sigma discovery at 2 energy stages for masses of the doubly charged Higgs. And what you can see is basically that even for masses which are close to the kinematic threshold, the required luminosity for the 5 sigma discovery are well below the integrated luminosity foreseen for click, which I've shown you earlier. So basically, we could catch these particles up to their kinematic limit. Finally, as I mentioned before, also thresholds can be quite useful. So here, I just show you one study, which is for right-handed muon pair production, where these muons decay to muons and missing energy. And what you see is in the top left, what happens if you would take some data at several energy stages around the pair production threshold, which in this model is assumed to be at about 2 TeV. And basically what you see in green and red are the threshold behavior of the cross-section. In one case, assuming we have a spin 1/2 particle, the other case where we have a spin 0 particle. And basically, we can translate this into an exclusion of the spin 1/2 hypothesis in the bottom left. So you can see that, okay, of course, as we have right-handed muons, the spin determination would benefit from positive electron beam polarization. And we actually also use this study to demonstrate the flexibility of a linear collider. So you can actually reduce the horizontal emittance of the beam with some penalty on the luminosity. But then you can really get a good separation of the two cases in such a threshold scan. And then we could, in the same way, also measure the mass of these particles with a precision of a few GeV, depending on how much luminosity you would actually take. Of course, we can also look for dark matter directly. I'm just going to show you one example using stub tracks. So this is as a benchmark model using Higgsino pair production, where the chargino and the neutralino have a small mass difference. So we basically just produce a soft pion and a disappearing track from the chargino, which here is required to leave at least 4 hits in the detector. So what's really important here is the vertex detector. And you can see in the bottom right, the 95% reach of click for various signatures. So if we require at least 1 short track or 2 short tracks, or a short track with a photon of various energies and so on. And basically what you can see is that the thermal Higgsino at 1.1 TeV is within the range of a 3 TeV click collider. So to summarize, I'm showing you here a table which contains all the examples which I've shown you, and in addition, a couple more ones. So in the cases where we can compare to the high luminosity LHC, in many cases, there's some substantial improvement possible with a high energy plus or minus machine. So to conclude, CLIC is a mature project. It could provide a Higgs and top factory, and then subsequently a multi-TeV lepton collider, which could provide substantial improvement for a wide range of BSM searches. There's a large amount of complementarity between direct and indirect searches. I've shown you a few examples, including the heavy scalar, and then also between the different energy stages. And of course, some unique features of E plus E minus are also beam polarization and threshold scans, which can help to understand potential discovery. Thank you very much.
Thanks a lot for this very nice talk. So now we have time for 1 or 2 questions.
Can I have a question? It's Michal.
Sure, sure.
I'd just like to ask about Z prime searches. I mean, there seems to be some affinity throughout the the community to consider Z prime coupled through the hypercharge. So I would like to ask, I mean, there is this very, very natural standard model extension in which Z prime couples to B minus L instead. So why this is not entertained?
So I don't know. So I think the example I've shown was used for the comparisons for the discussions in the European strategy, but we also have limits for a Z prime scenario where you basically have the standard model Z couplings, and there for a 3 TeV click machine we would get a reach of about 20 TeV.
Okay, thank you.
All right. Okay, then. Okay, now we move on to the next talk. So thanks, Philip. So Mikaya,
hi.
Maybe could you start? Yeah, hi. Could you start the share screen?
Yeah, sure.
Okay. So our next speaker is Mikaya Meland from Sun. We'll be talking about the phasor. So please go ahead.
Okay, so hopefully you see the slides full screen now.
Yes, and also yourself, yes.
Perfect, hi. So I'm excited to talk to you today about the phasor experiment or forward search experiment at the LHC. So to give a brief summary of what phasor is, it's a new small experiment which makes use of a unused service tunnel at the LHC, which used to be an old LEP injector tunnel, to search for long-lived particles produced in interaction point 1, otherwise known as ATLAS, at the LHC during run 3 and beyond. So the concept was first proposed in 2017, and it was approved officially by CERN in March 2019, although it's a small experiment with a limited budget of around 2 million. And it's to be fully built and installed during the current long shutdown, so by the end of this year, 2020. And so the budget and the tight timescale has driven a lot of the detector design and concept. So it needed to be constructed quickly and cheaply. So we reuse a lot of detector components. It has a simple and robust design since we will have limited access to the LHC tunnel itself during operations, and to minimize the services for ease of installation. So just to paint a picture of where phasor fits into the new physics landscape, so if you consider new particles in terms of their mass and their interaction strength, typically the traditional targets of big science, and especially at the LHC, tend to focus on strongly interacting heavy new particles. As you go to lower or higher interaction strength and lower mass, this is the picture that's already very well discovered. But then if you go to lower interaction strengths and low masses, you get into the region of weakly interacting light particles, which is in particular the target of a lot of the newer, smaller experiments, and this is where phasor fits in. So the main concept of phasor is essentially to look in the forward region at the LHC. So the large experiment searches, as I said, tend to focus for heavy, strongly interacting new particles, which tend to be produced at high PT and approximately isotropic. But if we say that new particles are light and weakly coupled, then the cross sections would be too low, and also the acceptance of the ATLAS or CMS detectors would be too low. And so we need to look for these in light meson decays, so for example in pion decays, and we need an extremely high rate in order to see them. And so the idea is to look in the forward region and benefit from the extremely high rate of hadrons produced in ATLAS. So just taking the example of pions, we expect most of the pions to be produced within a milliradian of the beam direction. And within run 3 of the LHC, we expect ATLAS to produce around 10 to the 16 such inelastic collisions. And lastly, the key point is that these light weakly interacting particles would travel macroscopic distances, so at least meters, but perhaps kilometers before decaying. And so the idea of phasor is to put a detector 480 meters down the beamline from ATLAS, which would cover, with a small detector of only 10 centimeters radius, a relatively large fraction of these pions that are produced within ATLAS. So we expect around 10 to the 17 pions within the phasor acceptance. So this is 2% of the total number of pions produced within ATLAS, despite the fact that the detector only covers 10 to the minus 6% of the solid angle. So there are many physics models that we would be sensitive to, but just to give one example of the physics potential is the sort of flagship dark photon model. So here we have a light weakly coupled mediator, which mediates between a new dark sector, which contains or could contain a dark matter particle candidate. And so these dark photons, denoted by A prime, are similar, interact similar to a standard model photon, but they can be massive, and they interact with standard model particles through a kinetic mixing with the standard model photon through this parameter epsilon. And so they can be produced, for example, in neutral pion decays, such as the example given here, and then they can decay into a pair of charged particles, which we could then detect. And so within run 3 of the LHC, we expect to see around 100 dark photons, assuming a mass of around 100 MeV, even with a very large suppression factor. So the LHC could really be a dark photon factory. And so what you see on the right here is the typical plane of showing the interpretations in these models, which is the kinetic mixing parameter on the y-axis and the mass of the dark photon on the x-axis. And you see two contours. So one is phasor, which is the proposed or the approved experiments that will occur during run 3. And phasor 2 is a proposed upgrade for the high luminosity LHC. But you see that with phasor, there's a large region of uncovered parameter space. So everything in gray is already excluded, and everything in the colored lines are proposed or upcoming experiments or projected limits. And indeed, we see that even with one inverse femtobarn of data that we expect to hopefully collect in 2021, depending on when the LHC starts again, we start to probe this new region. So I already mentioned that phasor will be located in an old SPS to LEP injector tunnel, so called TI-12. So here is ATLAS in the Meran site at CERN, and then this is the LHC beam pipe, and then phasor is directly on the line of sight with the collision point. It's shielded by around 100 meters of rock and concrete, and it has very low beam backgrounds. So the only thing that we have to do in the tunnel is to dig a small trench. This is 50 centimeters deep because the tunnel itself is sloped upwards. And so to be on directly the line of sight, we have this small trench. And you see two photos here of the tunnel itself. So this is before any work was done. And the bottom one shows how close this is to the LHC beam pipe. So we've performed both the Fluker simulations and in situ measurements to assess the expected backgrounds in the tunnel. The dominant backgrounds will be mainly coming from muons produced in collisions within ATLAS. Everything else is either deflected by the LHC magnets or is absorbed by either the TAN or then 100 meters of rock. We have extremely minor backgrounds coming from off-orbit photons, which hit the beam pipe aperture near TI-12, and sometimes beam gas interactions. But these are very small due to the LHC optics. And so what this means is that we expect very low radiation levels as well in the tunnel, and therefore phasor, unusually for an LHC experiment, phasor does not need radiation-hard electronics. And so you see here two examples of the expected fluence rates. This is for muons on the left and for neutrinos on the left and for muons on the right-hand side, where you see this fun feature that we expect a much larger number of negative muons than positive muons due to the nature of the LHC magnets. So the design of the phasor detector, so you can see here an overview. So an incoming long-lived particle or neutrino would come from the right-hand side. So this is going back to the ATLAS interaction point. And then we have 3 tracking stations, which are supported by a tracker backbone. we have three magnets, the first of which is a decay volume, and then the second two, which consist of the spectrometer. We have three scintillator stations, which are used for triggering, timing, and to veto incoming charged particles. We have an electromagnetic calorimeter at the back, and at the very front, we have an emulsion detector, which is used for the neutrino physics program, which I won't cover in this talk, but I encourage you to go see the talk by Aki, which was on Wednesday in the neutrino session. So just to give an overview of the different components of the detector, so each of the tracking stations consists of 3 layers, which use 8 spare SCT, Atlas SCT barrel modules. So thank you very much to the Atlas collaboration for letting us use those. These have a 18 micrometer strip pitch and allow around 17 micrometer track resolution in the sensitive direction. We then have designed our own custom support structure. So we have aluminium frames which support the modules, custom flex cables, and patch panels for routing the channels. And you see overlaid on this tracking layer in yellow, this is the aperture of the magnet. And so this is the most sensitive area for detecting our signals. We then have 2 photos of the tracking layer. So this is one without the cover on it, so you can actually see the modules and the flex cables and the patch panels. And then on the right-hand side is a photo of our first tracking station, which arrived 2 weeks ago and which we're now testing. Yeah. And so next we have the calorimeter and scintillator stations. So these veto incoming charged particles and are used for timing and triggering. So the scintillator plates themselves were produced at CERN, and we have a commercial K-on digitizer board to do the readout. The electromagnetic calorimeter, which is used for energy measurements and particle ID and triggering, is built from 4 spare LHCb outer eCal modules. So thank you very much to the LHCb collaboration. So this is a lead scintillator calorimeter structure, which consists of around 25 radiation lengths. And both the scintillators and the calorimeters were tested and characterized with cosmic data. So you see here the test stand that was used to test the scintillators, and here the custom stand that we built in order to prop up one of the calorimeter modules vertically so that we could take some cosmic data with these as well. So one of the main costs and structural parts of the detector are the magnets themselves, which were designed by the CERN team. So these are 0.55 Tesla permanent dipole magnets, which are based on an Halbach array design. So you see a photo of the first one that was constructed here in the top right. And so the magnets themselves are then secured to the tunnel floor using a base plate, which is connected through a mixture of grout and cement. And then the tracking stations are then mounted on top of these magnets using what we call a backbone. And then we have an upper support frame, which goes around the whole detector, which supports additional electronics and helps to route all of the cables. So our triggering strategy is to use an OR of the scintillator or the calorimeter. So we only expect a rate of around 500 Hertz in total, mostly coming from muons from the Atlas interaction point. In terms of picking out a signal, we will synchronize these with the LHC clock. Although it's important to note that we actually don't have to share any signals at all with Atlas. We will only use the luminosity calibration, which will be developed by Atlas. So we have custom GPIO boards, which we use both for the tracker readout and for the trigger logic. And as I mentioned, we have these commercial digitizers for the scintillators and the calorimeter. In terms of run control, we have a lightweight web-based system, which is based on the CERN DACling open source data acquisition framework. And our offline software is based on the open source Atlas Athena framework called Calypso. If you know your Greek mythology, Calypso is the daughter of Atlas. And so you see here one of the very first simulations of what a dark photon signal would look like in the detector, and on the right-hand side, a little bit more of a refined view of the tracker modules within the GEONT simulation. So the next couple of slides show a little bit the status of the commissioning and the surface dry run. So we have a dedicated lab area in CERN's Preveson site called EHM1, or the neutrino platform, which is also the location where ProtoJune is being assembled and tested. And we plan to use this for the full detector commissioning. So we'll build the whole detector there before we then disassemble it and transport it and install it into the CERN tunnel. So the dry run should be done around September once all of the individual components have been tested. And then everything has to be installed by around mid-October, which is when the LHC magnets will start to be cooled. And essentially once the LHC magnets start to be trained, we then have very, very limited access. And so this is really the thing that drives the deadline for installing everything into the tunnel. So I've just got some photos that I took last week of the area in Preveson. So I already showed the prototype tracking station, but we also have now this mock-up base plate installed in the lab. So we even have a 1% slope to this mock-up base plate to simulate the slight slope of the LHC. And we have the support structures for the scintillator stations, the calorimeter modules that are in place. And just on Monday, we had the installation of the first magnet. So this is one of the 1 meter long spectrometer magnets, which has now been installed there. There's also been a huge amount of work in the tunnel itself in terms of civil engineering. So you see a photo here of the tunnel site after it had been cleared, but before they started digging the trench. And you see this dust tent that had to be installed to protect the LHC. This is a slightly different view standing on top of the LHC. So we have a walkway that had to be installed over the LHC and a crane in order to move all of our components over the LHC. And then you see the tunnel itself before any work was done, and then after all of these unused services were cleared. And then in the last few weeks, the handling rails, so the cranes to install the detector components, and also the real base plate have now been installed. So everything's coming together nicely and yeah, starting to look like a real detector. So this brings me already to my summary. So PHASER is a new experiment at the LHC, which complements the current physics program and exploits a large number of boosted low PT inelastic events in ATLAS. It's small, it could almost fit on the tabletop, only a budget of around 2 million and 18 months from theory paper to start of construction, which I think is phenomenal. It's sensitive to many models of light weakly interacting new physics, such as dark photons, but also heavy neutral leptons or axion-like particles. It also has a very strong neutrino physics program, which has a dedicated emulsion detector for. So I would really encourage you to see the talk that I've linked to here by Aki on PHASER New. And I didn't have time to discuss today, but we also have the potential to increase the sensitivity during the high luminosity LHC with a PHASER 2 upgrade, which would essentially be a bigger and better detector. So data taking begins in 2021 or 2022, depending on the LHC schedule, and we're looking forward to new physics. Thank you for your attention.
Thanks a lot for this very nice talk. So maybe 1 or 2 urgent questions, if there are.
Yes, good morning. I have a question. Very nice talking, Hera. The question is very quick. Mm-hmm. Can you tell us a little bit about the lowest mass range for the dark photons, how sensitive you are, and the lowest level of the mass range? What is the lowest mass range you can detect?
For dark photons, so... Oh, for the dark photons.
For the dark photons, yes, maybe it will sound very good, yeah.
Yes, so I guess you're talking about the sensitivity curve that I showed.
Yeah, but
here?
Very quick. Yeah, somewhere there, yeah.
So what specifically is your question?
Yes, I mean, it's in the sub-GeV range, so how much sub-GeV we're talking about? That's my question.
Well, I guess you see the range here.
Yeah, okay.
I mean, so the thing is that we cut off the plot here because everything below this is either already excluded or PHASER wouldn't be sensitive to. So,
but you see more sensitive in lower masses than the higher masses, as you can see.
Yes, exactly. Yeah. So you don't even see, for example, the higher mass regions where Atlas and CMS are sensitive to. Yeah, exactly.
10 to minus 2, 10 to minus 1. Okay, thank you so much. Thank you.
Thank you. So for more questions, I suggest to utilize the Mattermost. Okay, thanks, Michaela. So now we move on to the next talk. So Sergey, could you start the share the screen?
Yes. Can you share my screen?
Yes, sure. Our next speaker is Sergey Shirobogov, who will be talking about the search for a new physics with the SHIP experiment at CERN. So please go ahead.
Yeah, thank you. Thank you for introduction. I'm a PhD student at Imperial College London, and today I will talk about the search for new physics with a SHIP experiment at CERN. Okay. Yeah, so SHIP is motivated by many theoretical models that predict massive particles that can be tested experimentally. And so this massive particles can interact with the current model via the mediator portal. However, this and thus we can make this hidden sector quite complex. However, these hidden sector particles production decay rates are strongly suppressed. So long-lived particles have small production breaking ratios, and they interact very weakly with matter. So we haven't observed them yet, but they may decay to various final states in visible sector, and they also may be produced in beauty and charm meson decay. So one wants to maximize the production intensity of B in D mesons to be sensible to the dark sector. That's why there was a proposal for the beam down facility at the SPS. So in the proposal, the nominal proton beam yield will be around 10 to the 15 proton target per spill. So this will result in about 10 to the 19 protons on target for the SHIP in 1 year. And while this will happen while respecting all the Halumi LHC requirements and the requirements for the experiment in the North area. So thus, in total, SHIP will be able to collect around 10 to 20 protons on target during 5 years of data taking. And this in turn will result in a large amount of B and D meson production, as well as tau leptons. Basically, there was a dedicated beam down facility feasibility study that was done by the CERN BDF group. And there is a massive yellow book published, the comprehensive design study of the beam down facility, which is 500 pages, and you can read it if you're brave enough. But overall, the idea is that the CERN SPS 400 GeV beam is very well suited to perform the SHIP physics reach. So how the experiment looks itself, the proton will be arriving here from the left to the right at the target. The target will be followed by the hadron stopper, and afterwards the muon shield will be located. After the muon shield, there will be a scattering and neutrino detector, and then it will be followed by the decay volume. And finally, after the decay volume, there will be a hidden sector decay spectrometer, which will consist from spectrometer, timing, and PID detectors. So basically, it can SHIP simultaneously operate in 2 regimes. It can search for hidden sector particles decay and the visible decays, and it can also search for the hidden sector and LiDAR matter scattering inside the SID detector. Plus, it can also perform a complementary neutrino physics inside the scattering and neutrino detector. So if you break it down to parts, then SHIP has a 12 interaction long PZM alloy target with a small interaction length. So to absorb pion and kaons before they are semi-leptonic decay. So the target is presented here at the left. This target will be followed by the magnetized hadron stopper to stop electromagnetic radiation hadrons that will be emerging from the target. But even with that, in SHIP, we expect around 10 to the 11 muons per spill to be produced in the target. And so thus to shield from these muons and sweep them out of the acceptance, we have a dedicated magnetic shield, which is 35-meter long, located here, straight after the hadron stopper. And this is actually very technologically challenging, engineeringly challenging object to construct. So we use various machine learning techniques to perform optimization of this object. And in its current state, we can reduce the 11 muons per spill to just 50 kilohertz, which is quite a small rate. So because the muon flux is such an important topic for SHIP, there was a dedicated measurement made of the muon flux at the test beam in 2018. And the main point was to validate Monte Carlo muon flux, taking into account the cascade production effect inside the target. So the experimental setup is presented here at the right. It was located at the H4 beamline at CERN SPS. And around 10 to the 11 proton targets have been collected on a SHIP target replica during the operation. So at the bottom, you can see the distributions of P and PT. And in blue, you can see the distribution obtained from the data. And in red, the distributions from the Monte Carlo simulation. And so as you can see, there is a good agreement between simulation and experimental setup up to 300 GeV. So if you are interested in details, there is have been a dedicated publication done recently, and the link is presented here at the bottom left. So in addition to that, there have been charge production cross-section measurement, which is important for dark sector and neutrino physics. And the analysis for this part is currently ongoing. So coming back to the detector, as I have mentioned, we can detect detector particles in two regimes. So if you want to decay the visible decay, we have a dedicated decay volume, which is 50 meters long. It has a low pressure inside and surrounded by the background tugger, so V2 standard model particles entering the decay volume. Afterwards, we have a magnet spectrometer to reconstruct the momenta and the decay vertex position. Afterwards, there is a timing detector with a 100 picosecond resolution, so where it can help us to suppress the combinatorial muon background. Then afterwards, there is a ECAL with a tracking capability of a couple of millirods, and this will help us to study the signal from axion-like particles to photon decays. And finally, there is a muon filter for flavor identification. So we know the mass, charge, and flavor of the decaying products at the observation. There is also the scattering neutrino detector. And the scattering neutrino detector is an emulsion detector. So it consists from emulsion cloud chamber, which is an emulsions interleaved with lead and has 5 spatial resolutions to observe tau decay vertices. This emulsion cloud chamber is placed inside the magnet, so we can distinguish charge, which we can identify charge, and then we can distinguish between neutrinos and antineutrinos. And this SND detector will be performing the neutrino cross-section measurements and also first direct observation of anti-nu tau. But also you can search for light dark matter via scattering in this detector. So basically, the light dark matter will be traveling to the detector, scattering of the dense material of the detector, and the signature will be an electromagnetic shower here with a clean vertex. And the background will be coming from neutrino CC and CK interaction. So there have been a dedicated talk on this by Marlise Deserio on the 29th. So you can refer to this talk also for the details. But speaking about background SHIP, there are 3 main sources of the background. So first is the neutrino induced. Neutrinos can originate in the target, then travel towards the direction of the hidden sector detector. And then they can scatter in the air on the proximity inside the decay volume or in the proximity of the decay volume. But the rate of such events found to be negligible with a small pressure inside the decay volume. However, there is always, of course, a second background that the neutrinos can travel to the direction of hidden sector detector and then scatter off the dense material. So it could be SND, it could be experimental Hall walls, or the decay volume walls. And the number of events estimated in 5 years is around 10 to the 5. But however, this background can be further suppressed after applying selection cuts, and the estimated background is around 0.1, 0.3 events after a selection in 5 years. The second source of the background is muon inelastic scattering. So also muons produced in the target can scatter off the dense material like SND or decay volume walls. And again, applying the selection and background tagging, it's possible to reduce the number of such events to 10 to the -4 events in 5 years. And finally, there is a muon combinatorial background. So muons produced in the target can travel inside the decay volume, and then they can create fake decay vertices inside the decay volume. So to protect from this background, obviously we need our muon shield. Second, we need to have a slow beam extraction from the SPS. But even with this, we can have a 10 to the 16 pairs of tracks during 5 years of operation. However, applying various selection cuts and using time detector, we can reduce the number of these events to 10 to the minus 2 in 5 years. So thus, the SHIP is planned as a zero background discovery experiment. Now talking about sensitivities, SHIP is sensitive to various theoretical models in the big parameter range. So for example, there is a neutrino model where heavy neutral leptons will decay in heavy flavor decay inside SHIP target and then can be subsequently detected in the downstream spectrometer. And here SHIP has a very good sensitivity below the B mass, and in this parameter range, it outperforms other planned experiments. SHIP is also sensitive to a vector model, so namely dark photons that can originate, as was mentioned before in the previous talk, from meson decays, Bremsstrahlung, and QCD inside SHIP target, and then subsequently detected in the downstream spectrometer as well as decay of leptons to leptons. And in that case, the sensitivity is present here on the right. SHIP is sensitive to the up to mass of dark photon about 5 GeV, and in that sense, it's by orders of magnitude outperforms other planned experiments. So in addition to it, SHIP is also sensitive to other theoretical models such as scalar portal or axion-like particles. So they both will be produced in the B and K decays inside SHIP target, and then detected in the decays to leptons or hadrons in the downstream spectrometer. And in case of the scalar portal or the axion-like particles coupled to fermions, the SHIP sensitivities will be comparable and complementary to other planned experiments. And in case axion-like particles that are coupled to photons, and the sensitivity to this is present here on the right, SHIP also will have a very good sensitivity to the up to the mass of axion-like particle of 1 GeV. And this all thanks to the directional, to the ECAL with the directional information. And finally, SHIP is also sensitive to light dark matter via scattering. So the light dark matter produced inside the target can travel some distance, cross the muon shield, and then scatter off the dense material in the SSD detector. So as I have been mentioning before, the signature in that case will be an electromagnetic shower that can be detected inside the emulsion. So in that case, the background will be coming from neutrino elastic scattering events. And so this is background, of course, is reducible, and we need to apply kinematical cuts, or the quasi-elastic scattering of neutrino. And this background will be also reducible in case the secondary particles are soft and they will be not identified in emulsion. So the sensitivity to light dark matter is presented here at the left. So in that case, SHIP is sensitive to the mass range of dark matter from 1 to 500 MeV. And the limits it can impose are either superimposed or very close to the theoretical limit. So this brings me to the conclusion that no new physics have been discovered after LHC-2, and thus diversifying the physics program is very interesting. The beam down facility at CERN is a very ideal place to search for new physics for SHIP because it has a high energy and high intensity SPS beam, and this is minimal modifications to existing facilities. Direct observation of hidden sector decay vertex and light dark matter detection via scattering are being explored by SHIP simultaneously. Plus, SHIP also has complementary neutrino physics program. So SHIP is a discovery experiment because it's equipped with spectrometry, PID, and zero background expectations because of the background tagging system and event selection. It can also host the BDF, the beam down facility, can also host other experiments after SHIP or at the same time. For example, tau flavor experiments can run in parallel, exploiting very high production rates of tau leptons. And finally, there was an SCP update. And given the positive SCP update about SHIP physics program, the SHIP collaboration is now awaiting the decision from the CERN management. So that's it. Thank you for the attention.
Thanks a lot for this very nice talk. So are there any questions or comments?
So can I perhaps ask a question? It's Michal.
Sure, sure.
Yeah.
Am I right that you said that it's going to be a magnetized experiment, right? I mean, your detection volume is magnetized.
No. Detection volume is not. The decay volume is not magnetized. The magnetized volume is for the scattering neutrino detector. So here we have the volume is magnetized, but further down, no.
I see. Okay. Okay. Thank you.
Okay. So are there other questions or comments? If not, we can move on. Thanks, Sergey. All right. So now our next speaker is Emma. So Emma, could you start the sharing?
Hi. Yes, I'm just trying to share.
Yeah, our next speaker is Emma Toro, who will be talking about the exploring the lifetime frontier with the proposed Mashouba experiment. So please go ahead, Emma.
Okay, so I understand you can see the slides, right?
Yeah.
Okay. Yeah. Oh. Wait a second, because it's moving without my permission. Okay. Yeah. So the first. So Methuselah is a proposed detector to search for ultra long-lived particles that could be generated at the LHC or high luminosity LHC. And then the first question would be, why do we need such a detector? Because we have already the main LHC detector, which have a wide program to search for long-lived particles. But however, these detectors and these searches have a number of limitations. First of all, for example, events have to pass a trigger, and if they don't, they are lost. And mainly they have to deal with a lot of backgrounds, both from collisions, including pileup, which for the high luminosity phase will be really, really important. And also from direct backgrounds from the beam. And in the end, they are limited by the size of the detector. So even if we search for a large number of unconventional signatures, the LLP could decay outside the detector, and then these detectors would be completely blind to them. So a detector which is working in a background-free environment would have a lot of sensitivity, and Methuselah is designed to be such a detector. So the aim is to reach the Big Bang nucleosynthesis limit in lifetimes. And for this, we need a very good sensitivity. And this means that we need to suppress the LHC backgrounds. So in this dedicated detector, which will be placed on the surface above CMS during the high luminosity LHC phase, we already have about 60 meters of rock, which act as a shielding, and this reduces a lot the backgrounds from the LHC. So the concept of the detector is a very simple thing. So we have a large volume filled with air, and this acts as a decay volume. And then we have several layers of tracking. So on the left in this sketch, you can see the kinds of signals that we expect. So the neutral long-lived particle generated in the collision would fly and decay inside the decay volume, and then the tracking layers would reconstruct the tracks. And on the right, we have the different kinds of backgrounds that we can expect that I will comment a bit more on later. So for this, to be able to distinguish signal from background, we need a robust tracking to be able to reconstruct the vertices. And we also need good timing to be able to distinguish upward going tracks from signal from downward tracks coming from cosmics. So this is the baseline detector design. It's going to be a large detector. It's 100 meters times 100 meters on side and about 25 meters high. And this is the CMS site. This star here corresponds to where the IP would be underground, and the blue building is what the Methuselah detector will be. So yeah, the idea is to construct it in modules, so it's easier to adapt the shape to the available land on the site. And then it also allows for staged integration and ramp up. So part of it, most of the decay volume will be underground. We will excavate a few meters. And then the main tracker layers will be on the surface. So we have 3 sets of tracking detectors. We have 2 layers of detector on the floor, and this will act as a veto to every charged particle that comes from the LHC collision. And then we have 5 layers of tracking on top and 2 intermediate layers of tracking also. And this has been placed at a distance that is optimal for the performance of the tracking. the backgrounds that we can expect are mainly two components. One is everything that comes from the LHC collision. So we can have muons going directly through the detector. They can also do inelastic scattering, or we can have also neutrinos coming from the LHC and decaying and giving, or scattering and giving tracks, upward tracks. So all of this can be rejected with the veto layer we have on the floor. Then we have cosmic rays going downwards, and this can be rejected because we have good timing resolution that is able to distinguish upwards from downward going tracks. And then maybe the trickier one is the atmospheric neutrinos that will look very similar to the signal that we expect. But this, the rate we expect for this is very low, and they are very low momentum particles. So they are non-relativistic, and we can use the time of flight to project this. So talking about sensitivity, yeah, as I said, we are aiming to be a near to zero background detector. And in this plot, I'm comparing the sensitivity expected for the Atlas analysis that it has a largest coverage in lifetime to the sensitivity expected for Methuselah in the high luminosity phase. This is for an exotic Higgs decaying to two scalars, which are long-lived and eventually decay to hadrons. So just because we are a background-free experiment, we have a very large gain in sensitivity of several orders of magnitude. And because of the size and the position of the Methuselah experiment, we also gain a lot in the range of C-taus that are covered, reaching or approaching the BBN limit. So this sensitivity I'm showing here is comparable to the one we had for the original benchmark, which was 4 times larger in size. And we've accomplished this by bringing the detector closer to the IP. So vertically, as I said, we will excavate a bit so part of the detector will be underground, and also bringing it closer horizontally to CMS. About the hardware we are planning to use, we will use scintillators for tracking with wavelength shifting fibers, and at each end of the fiber we will have a silicon photomultiplier. We can use the time difference to get a longitudinal position. We also considered having RPCs for tracking, but in the end we decided to go with scintillators, and there are some advantages over RPCs. So for example, we don't need high voltage or gas to operate them, and they are also stable with temperature and pressure. And now I'm talking about the results of the test stand. So the test stand is a small scale experiment that we built on the surface of the Atlas detector. It was built in 2018, and it was taking data both when the LHC had collisions and when there were no beams running on the LHC. So this is the layout of the test stand. We have the Atlas detector here, and the test stand was placed on top. So on the surface, more or less on top of the IP. It was made of several layers of detectors. We had scintillators on the bottom and on the top part of the detector, and then we have 3 double layers of RPCs that were used for tracking. So we used the scintillators, so the top layer and the bottom layer, to define triggers. We had one trigger for downward going particles and another trigger for upward going tracks. And yeah, so here you can see how we could reconstruct, using all the layers of detectors, we could reconstruct both downward going particles and upward going, and we could distinguish this with timing, which is, the resolution is quite good for the RPCs we were using. So first we analyzed the data in LHC runs with no beam. And then everything we see in data corresponds to cosmic muons. So we have standard cosmics going downwards. And here on the left, you can see a distribution of the zenith angle. So the black dots correspond to data, and the yellow distribution is the cosmic ray simulation we did. And you see that the agreement is very good. And then we have a second component, which is cosmic rays hitting the floor and backscattering, and this can create upward going tracks. We also reconstructed this, and you can see the results in the plot the green one. So again, black dots are for data, and the green distribution is the simulation we did for this backscattering. And again, the agreement is very good. Then we moved to analyze the data when the LHC had collisions. And here I'm showing the results for upward going tracks. So again, we have two sources of background here. We have the same inelastic backscattering from cosmic rays that I showed before here in blue. So in these ones, you see that the zenith angle distribution is quite wide. And if we plot the rate of this kind of tracks as a function of the integrated luminosity in Atlas, you see that the distribution, so the fit we can do here is a linear fit, which is not dependent on the luminosity. And that means that, yeah, in fact, these events are not related to beam activity. The other component is muons coming from the LHC, and is this orange distribution here. You see that the zenith angle distribution is much narrower, and this is due to the small solid angle that is suspended between the test stand and the IP. We only are accessible to very small zenith angles. And if, again, we plot the rate of this kind of tracks as a function of luminosity, we see that they scale linearly very nicely, with luminosity meaning that, or pointing that these tracks are related or come from LHC events. Again, we did a simulation of these kind of events, and we see quite a good agreement between the simulation in orange and the data, which are the black dots. So this is a very nice confirmation that the background assumptions that we did for the Mathusla proposal are correct, and gives some confidence on the physics reach for the big Mathusla detector. I just want to give a last word on cosmic ray physics, because of the position on the surface of this experiment and the large area that it covers, this makes Mathusla a perfect detector for cosmic rays. So the baseline detector that I described already has some sensitivity and is useful to cover some energy spectrum for inclined cosmic ray showers. And now we are studying how to expand the potential we have for cosmic ray physics. So for extensive air showers, which are very dense, and especially if they are more vertical, we are studying the possibility of including an RPC layer, which would enhance a bit the detection of these extensive air showers. We are closely collaborating with cosmic ray experts. Yeah, so we'll see if this we can improve the coverage in cosmic ray physics with this idea. Yeah, so to summarize, we have the proposed Mathusla detector, for which we build a test stand to confirm the background estimations or assumptions we did for the Mathusla experiment. The results of this test stand are now public in arXiv, and they have also been submitted to NIM. And yeah, so they confirm that the background assumptions done for Mathusla are correct. For the main Mathusla detector, we have the baseline design is more or less established now. We're studying the performance of several hardware components, and we're also trying to study the possibility of increasing the reach to cosmic ray physics, which is a guaranteed physics payoff. And yeah, we are working closely with cosmic ray experts just to take the better, to make the better use we can do for this experiment. And we are currently working on finishing the TDR, which will hopefully be ready, hopefully soon. Yeah, so my last slide is just some documentation in case you want to read a bit more about the Mathusla detector. And that's everything from me.
Thanks a lot, Eva, for this very nice talk. So are there any questions or comments? Maybe one or two?
I have a small comment or question to the presentation. I think that the angle of incidence for the incoming and outcoming inwards and outwards beams plays any role to you? I mean, you apply some cut there? in the angle distribution, because I saw that the cosmic rays are more steeper and more perpendicular, but also maybe the muons who's going upwards have a similar effect. How you deal with this in the CATS level?
These ones?
Yeah, some of them. Yeah, you can see the angular distribution that we have on the left-hand side plot.
Yeah.
There is a different cosmic rays, and the IP muon, you can see clear peaks in the different angles.
Yes.
Which actually maybe then you can play different cuts in the angle just to reduce the background that's coming from the cosmic rays or whatever it is.
Right. So
that was my question. How you deal with this thing?
Well, so the idea of this test stand was just to kind of confirm that the expected number of muons coming from the LHC was what we thought it would be. So we are not so much interested in removing this kind of events for this study. I'm not sure I understand the question.
Yeah, I mean, you can distinguish. My question is very. Let me form it differently. You can use different angles of incidence from the upward and downstream and upstream beams, just to make a separation between what comes from the sky and what comes from the detector. That's roughly my deal.
Yeah.
The angles are different. I think that the angles that we have here from the IP muons are much steeper than the cosmic rays.
Sure.
The cosmic
you can
rays
see
are more broader distribution than the
exactly.
IP muons. The muons are more focused, that I say. So these are two different things.
Yeah, this is what you can see on the plot on the left.
Serves very well as a cut also in an angle. I will say above, let's say 5 degrees. Let's reset things, and that make the things in your distributions more easy to get rid of the background, which comes from the muons, from the cosmic rays. Sorry.
Yeah. So this more or less what we did to get this plot here. So in the plot here, the red line corresponds to everything with an angle less than 4 degrees. And that is what you see, that scales linearly with luminosity. So that's the thing that comes from the LHC. And everything with an angle higher than 6 degrees corresponds to the blue line here. So
it's very well distinguished and clearly view about what you're talking about.
Yeah.
Okay, thank you so much. Thank you.
Yeah, sorry I didn't get the question at first.
Okay, so now Tova raised her hand, so maybe Tova?
Yeah, thank you. So I'm curious on slide 7, like I know there's been some discussion about timing in with CMS, so you can use the data from CMS. Do you have any sense for how that might expand the lifetime reach in this plot? Like would it significantly change the lifetime reach if you could maybe, for example, use the entire volume of Methuselah, like meaning use the instead of using them as a veto, the bottom layers, using them like accepting those events because you have the timed in information from CMS?
I don't have a number for that, but yeah, I guess you would extend it to lower C-taus, and yeah, maybe it gets to a point where either CMS or Atlas can have similar. Yeah, I don't know. I don't have a number. Sorry.
Just curious. Thanks.
So maybe for the discussion, I can go to the Matamos, and then now I saw Alexander also raise his hand.
Yeah, I have just a small comment to this angular distribution on page 13. It would be probably very interesting also to see, for example, if you could plot the distance of closest approach of a track to the interaction point, then the separation could be even cleaner. Just if you reconstruct a track, you could just calculate the distance of closest approach to the interaction point, and then the separation should be very clean and this could also be easier extrapolated to the full size of the detector.
Okay, that's something we can consider. Thank you.
Okay, very good. So thanks, Emma. So we should move on. So Pavel, maybe could you start sharing your slides? Okay, so our Pavel?
Yes, I'm here. One moment, please.
Yes, very good. So our next speaker is Pavel Sopinski, who will be talking about the simulating hard photon production with withered.
Okay, thank you very much. First, good morning or afternoon, and I would like to thank the organizers for the possibility of giving this talk on the results, which are the collaborative effort of the people listed in here. And without further ado, let's go to the outline. First of all, I would like to first I will talk about the motivation for the analysis and for the results presented in here. And then I will present some of the things when it comes to the simulating monophoto events with Wizard. More on the details could be found in the presented paper, which just recently got published. And then I will talk a little bit about the prospect and future use, especially when it comes to the indirect dark matter searches. Okay, so the motivation was that many models, when it comes to the E plus E minus collisions, consider the possibility of direct dark matter production. Although, as actually Philip Roloff nicely said in his presentation, the center of mass energy would be very crucial to extend the range of the mediators that could be used or tested. And of course, in most of the cases, dark matter candidates couldn't be seen directly. So one of the promising channels when it comes to the indirect dark matter searches is the monophoto type of the events. And in this case, if we look at the pseudo diagram on the right-hand side, we could try to make the experimental-like approach and set some limits on the cross sections and make it a function of the mediator mass or width. The example of the signal, which would look like, for example, for the free TeV case for the click energies, and the dark matter mass of 50 GeV, mass of the mediator equal to 2 TeV, and the width of 50 GeV, you can see that one can see the very nice peak on the right-hand side. And having the model for the signal, one would like to have the realistic background description. And the background it would be nice if the background could be treated in the same way, especially because of the fact that there are some non-trivial issues that should be solved in this case. So the main sources when it comes to monophoto events, the main sources are the neutrino production and the Baba scattering. And one thing that should be noted in here is that what one would like to see in the detector is the matrix element photon. And still, we would like to keep the parameterization of the soft photon emissions called ESR photons, especially that they modify the available center of mass energy for the dark matter production. And the issue which should be solved in this case is that one would like to avoid double counting of those two sources of photons. And since we are keeping the ISR photons and also keeping in mind that it's the parameterization, it's good to know and keep in mind that Wizard ESR structure and functions, they have problems with describing the T-channel W radiation. It's a small fraction, but still, nevertheless, should be kept in mind. But as I would like you to, I hope to convince you that the outcome of this approach is the procedure which is general enough for any BSM searches with similar type of events that would use the neutrino and Baba backgrounds in their analysis. So if we go further to the how one could simulate monophoto events with those backgrounds, first I would like to define two key variables called Q minus and Q plus. Actually, they use the two main information coming from each photon in the event, each photon present in the event, which is their energy and their angle. We also use the energy of the electrons and positrons, but we keep them fixed as the beam energies. And to present you the case for 500 GeV center of mass collision, the plot on the right-hand side, you can see actually the regions, the solid lines, colored solid lines, represent the various ranges of the different detectors, subdetectors, and the requirements for the minimal energy of the photon. If you look at the inclined dotted green lines, that actually they present the cuts, the possible cuts on the PT of the photons, and the black and red dashed lines represent the two different regions. The red one represents the region which could be used to merge the ESR photons. So actually, it's the border between two regions. The lower region is the region for the ISR photons, and the matrix element photons ideally would be in the detector, in the range of the detectors. And to do so, there are two variables defined, which is the minimum energy and Q minimal, which should be applied for each of the matrix elements. And having those two variables, we would exclude ESR photons, which would be above those two values. And since we would like to treat the BABA background also, one would need to make the selection in which we select at least one hard photon. Otherwise, the cross-section would be infinite. And for further use in this talk, the hard photon selection is the selection in which we require one photon, at least one photon, and this photon should have PT greater than 5 GeV and the defined theta range. Okay, so having those two variables defined and the phase space more or less described, one can test how actually the merging procedure if the procedure can distinguish those two sources of the photons. And as you can see, the red dots represent the ISR photons, the black dots represents the matrix element photons for the neutrino sample with the hard photon selection. And in here, those events were generated with the Q mean equal to 1 GeV, and one can see the nice curve for the theta requirement, and also here you can see the nice border for the minimal energy requirement. The plots are presented for the click free TeV case. If you would like to see the BABA, the similar plots for the BABA background, you can go to the backup slides. Okay, so how this works with changing the minimum Q mean value if the procedure is stable enough. You can see, first of all, on the left-hand side, the plot for the distribution of the PT of the photons with different Q values for the neutrino background. The normalization is that we have the number of events for the integrated luminosity of one inverse femtobarn. On the right-hand side, you can see two tables for selected center of mass energy. And you can see that the obtained cross-section values are more or less are very stable when it comes to also the for two different scenarios with the hard photon and without hard photon selection. Similar tables are in the background when it comes to the different energies for different experiments, proposed experiments, and also for different center of mass energies when it comes to click. There are also tables for free TeV cases. And if we go further, here are some plots for the BABA case, and one can see that the comparison of the PT spectra for neutrino and for the BABA backgrounds for different energies actually gives us a very stable and nice results, and the distributions show very small impact on the of the selection of the Q parameter, and there was one value chosen for the further analysis, which was set to 1 GeV. Okay, so one way of comparing the results, how well can they describe the processes, the background and the later use for the dark matter processes. We use the KKMC generator, which is a semi-analytical, which uses the semi-analytical approach and is very nicely tuned to lab data. And basically, one can see on the left-hand side that it generates a lot more ISR photons. The distribution for the number of photons in each of the event is very different. But if we apply the same procedure and we use the hard photon selection on both of the Monte Carlos, we actually get a very nice description between those two Monte Carlos, except for the higher multiplicities of 3 or 4 photons. There is a small discrepancy, but still the distribution for example, for the PT of the photon agrees very nicely. So having the procedure, we can now check how it compares the signal and how the backgrounds actually would look like. And for the already mentioned experimental-like approach, we present you the two-dimensional distributions of the energy and the eta of the photons. And if we look at the case for the free TeV click, one can see that the separation between signal on the right-hand side and backgrounds, the sum of the backgrounds on the left-hand side, is very nice. Although one can also see, especially if you go to the backups plots, one can see that the width parameter is very crucial for this type of the analysis, and this can be tested how the limits would behave when we change the mediator masses, dark matter candidates masses, and the widths of the mediators. Okay, so I hope that I convinced you that this procedure of merging two sources of different two sources of the photons allows actually to treat. It describes backgrounds very nicely and allows us to use this type of events, monophoto type of events, in different arbitrary BSM scenarios, and that this procedure works nice enough to allow us to obtain model-independent limits on dark matter, indirect dark matter searches. And two things to be noted in here is that this procedure only needs the coupling structure, not the exact values of the couplings, which is very nice. And also, which I already presented on the previous slide, it can test the impact of the mediator width and masses on signal to background separation. And that is all I would like to present for you today. Thank you for your attention, and I'm waiting for your questions.
Yeah, thanks a lot, Paweł, for this very nice talk. So any questions or comments, maybe one or two urgent ones? Yes, Michael?
Yeah, it's very nice talk. So I suppose you have communicated this method to the wizard authors and
yes, we've already did. Yes, we were in contact with them. Yes.
Yeah. Okay. Very good. Because this seems something that should be generally known in the ± community how to do this. And with this, okay, very good. Thank you.
You're welcome.
Okay. All right. Thank you. So so now we should move on to the next talk. So thanks.
Thanks a lot, then. Bye.
Yeah. So Aaron, maybe
yes.
could you start sharing the screen?
No problem.
Yeah. Yeah. Our next speaker is Aaron Paul O'Neill, who will be talking about when jets meet Suji, I think. Yeah. So please go ahead.
Yeah, so I'll turn the video on. I'll copy Michaela, and you can see my face if you want. Yeah, so that's right. I'm going to talk about these atlas searches for squarks and gluinos, but the talk is kind of divided into two different parts. I'm going to start off talking about some of the performance work we've been doing, and then how this eventually contributes. So after hearing about all of these nice new experiments coming down the pike, we can see what we've been up to in Atlas. Okay. So I'm sure you've seen this plot 1,000 times, and my apologies for that, but this is the delivered luminosity against the month and the year. So the point of this is that Atlas has recorded a phenomenal amount of data in run 2. And the question from the SUSY group is, could supersymmetry be hiding in this record-breaking data set? So as I said, I'm going to present these improvements firstly in jet reconstruction and then missing transverse momentum and its calculation. And then I'll show 2 analyses that show how these improvements have contributed to our sensitivity and eventual exclusions. Okay, so just to jump straight in with the jets and ET miss, just a quick note on the format. So in the bottom of each title slide here, I've linked each of the papers that you can have a look at. And then on each slide as well, I've put the reference for the relevant material. Alrighty, so just starting off at the very beginning, jets are extremely important objects in the Atlas detector. So it's very critical that we can understand them and calibrate them properly. And in the simplest terms, you know, they're just collimated sprays of particles, hadronic matter, that we can measure in the Atlas detector. And I'll talk about how we actually do measure that. And there's been a really interesting paper that's come out recently on the energy scale and corresponding resolutions for jets. This is measured using some of the Atlas data set, and I've linked it below if you want to have a look. But first of all, let's look at the particle flow jet reconstruction. So now in Atlas, it's increasingly common for us to use particle flow jets. And these jets are a little bit of an upgrade from the EM topo, the topological cluster jets, in that we now combine track information with the calorimeter clusters. So this is basically with the purpose of giving us increased performance at low energy due to the superior tracker momentum resolution. And I put in the various terms for this here in the bottom right. And then at higher energies, you know, we switch over to the calorimeter due to its increased energy resolution there. But the main point of this is that we get better pileup suppression, which is very good, especially in searches involving many jets, and then also an improved angular resolution for particle flow jets. All right, so just to quickly flash this plot up, this is the jet energy resolution against the PT of the jet. And we can see that at low PT, indeed, this is the case, the blue P-flow curve is below that of the EM topo. I'll not go into too much detail on this because Eva Hansen, which I've linked here, has a really, really nice talk, and it goes into the full details of particle flow and its comparison with EM topo much more thoroughly than I will do. Okay, and then just to push my point a little bit further, we can look again and see the absolute uncertainty in these jets, again against PT on the left-hand side. And the same thing occurs, reduction in uncertainty at low PT for the particle flow. And then as we go up through the PT spectrum, we see that the EM topo and particle flow jets become equivalent. And this is again, because of the reasons I've mentioned before, the tracker eventually doesn't contribute to the reconstruction of the jets. And then again, just to highlight my point of the angular resolution, this is a plot in eta and the corresponding uncertainty. So we can see that across the majority of the eta spectrum, we have this lower uncertainty for the particle flow in green. Okay, so that's the jets covered, well, loosely. But another really important quantity is this missing transverse momentum, or ET miss, and I will sometimes call it MET out of habit. And this is something that we can calculate, and it's a measure effectively of the missing, of the transverse momentum carried away by undetected objects, invisible particles. And there's only one known type that does this, and this is the neutrinos. So, but importantly for new physics, in particular SUSY, a great many of these models require that there be some form of stable invisible particle that can carry momentum away. And I've popped in this event display, which is of a 13 jet event recorded in Atlas. And we can see the nice reconstructed MET in red here. So this is the missing energy, which would suggest some sort of neutrino or new physics. All right, so we're just going to go through the definition so that we all know what I'm talking about. So this ET miss for Atlas is a negative vector sum of all of the reconstructed physics objects, which we'll call the hard term, or PT hard. And then the remainder of this is the soft term. And just to expand a little bit, so these are reconstructed and calibrated objects from a hard scatter in the experiment. And the soft term is all remaining detector signals not associated with the physics objects, but associated with the same scatter. So just to elaborate what I mean by this, is we can reconstruct it in a few different ways. So the first way we do this is the tracks from the inner detector, or ID, form the track soft term, TST. And the second way we can do it is from calorimeter deposits, or topoclusters. And this forms the CST, calorimeter soft term. For the rest of the talk, we will just focus on the TST due to its increased pileup resistance and overall better performance. Okay, and then just to look at some results that we've had from the MET performance group. This is a plot of the missing transverse momentum, but using a selection of Z decay to electrons. And we've put in the entire run-to data set here. And we can see that the data agrees with, in black, the data agrees very well with prediction. And this is only statistical error here. So the main point of this is that this channel, as we've selected it, should have no real MET. So we can see that at the low values of ET miss, we've got a very high contribution from ZDE, and then it drops off by several orders of magnitude very, very quickly. And then in the tails, we have actual real MET. So these TT bar and diboson processes start to contribute more and more, and to actually have neutrinos in them. And in the backup, I have some Feynman diagrams loosely explaining why this is the case. But I think it's fairly obvious, improved modeling of this ET miss is going to increase any potential for discovering physics beyond the standard model, and in particular, these invisible particles. Okay, but once we've calculated the MET, the next question is it real? Do we know it's an actual invisible particle and not just some resolution or mismeasurement effect? We can do this by defining this new object-based ET miss significance. And I should say that the object-based part comes from how we constructed the vector sum previously. So you see all the objects lined out, and then we define this significance, which is the magnitude of the ET miss vector squared. And then on the bottom, we have some variance terms. So I've put a little note in the top right to explain what I mean here. We've got some longitudinal variance, which is parallel to this ET miss vector, and then a transverse component as well. And then we've got this correlation. So this is the true definition of a significance, in that we've got this variable in the numerator and then some description of its variance in the denominator. And if you want to think about it in statistical terms, it's effectively an event by an event evaluation of the p-value that this observed MET is consistent with the null hypothesis that there's no real or true MET. And then just when we're looking at the plots later, just to give you a sense of what's going on, these low values of this variable indicate that the ET miss is resolution or mismeasurement, and then high values indicates that it's probable that there's a real invisible particle in the event. Okay, and then just to flash up a similar plot, we can see that we have nice agreement here again with this variable. And so up to these higher values, we would say that there's a very high probability that there's an invisible particle. And again, I think this is quite obvious, contributing towards the searches. We can reconstruct it better, and we can tell if it's real. So all of the uncertainties for this term actually are calculated separately for each object, but one that isn't calculated is the TST, the track soft term uncertainty. And we can do this by balancing this PT hard vector that I showed before against the soft. And ideally, especially in ZDE, we would have this complete balance. There's everything balances out quite nicely. But this isn't always the case. So in order to quantify this uncertainty, we can look at this parallel scale and then two different types of resolution, transverse and parallel. And just to quickly show what I mean by this, on the left-hand side, we have the EM topojets, and these are the various terms contributing to the track soft term uncertainty overall. We can see it's dominated by this parallel term. And a really nice result is that the particle flow jet suppresses this uncertainty very nicely indeed. Okay, so that's the first part. We've looked at the various performance work and how we reconstruct these variables. But next I'm going to talk about how this actually translates into searches for SUSY. And I'm going to start off with this analysis here called the TT2 lepton plus ET miss analysis. And in this case, their objectives are to use the full run-to data set, so this 139 inverse femtobarns, and include the object-based ET miss significance. So they've got a few target regions, but it's mainly for this top squark pair production, which decay through various modes, and they split this down by how many bodies are in the decay. So they start off with a 2-body. We see that the stops decay quite nicely into a top, and then the LSP. And we can just add more and more particles into the final state and step up through these different signal regions. They're also sensitive to this spin zero dark matter model, which actually falls into the two-body stop decay. You can see it's quite similar in its arrangement. Okay. So each signal region is sort of selected to increase separation between standard model and signal. So for example, there's some variables they have to constructed from ETMIS and the PT of leading leptons and jets, and it's to reject, say, Z plus jets or TTZ backgrounds and separate out the signal. So we can see again now that how we're already starting to contribute with the ETMIS improvement. But the basic selection of the analysis is 2 leptons, some jets, and then this ETMIS has to be of a certain value. All of the tables and details of the analysis are in the backup if you want to have a look at exactly what they're doing. But each of these n-body regions is, it's selected based on the topology of the model. And I've just quickly put in this 4-body summary plot. So we have the control regions they use with the various scaling factors for each background, and then a set of validation regions. And finally, on the far right, we have the signal regions. And as has been the case so far for all of our searches, the data is found to be consistent with standard model predictions. And what we do after that is then, if we can't find anything, we're going to make some exclusion plots and see where the masses are likely not to lie. So just to quickly show you this, we have their old limits in gray here. And this is the mass of the stop against the mass of the LSP for this double stop production and decaying by each method. But there's been a large increase in their exclusion, and this is in part due to the ETMIS significance. Okay. So another analysis that's been using some of these new techniques is the SUSY multijet zero lepton. And this is an analysis that has quite a lot of jets in the final state signature. So they require at least 7 jets due to these long cascades. And they're looking for production not of the stop, but of gluinos, which should have a large cross-section in a hadronic collider. And then we're decaying to this long cascade, which gives the many jets. They also use this B tagging for heavy flavor models. So they require integer numbers of B jet multiplicity between 0 and 2. And also, again, we're seeing this missing transverse momentum, which is a sort of through theme and why we need to think about how we reconstruct it. There's also a bit of a jet reclustering technique that is used in order to access the sort of the very, very massive gluino scenarios. Okay, so the objectives of this analysis are somewhat similar. They're using the entire run2 data set, but interestingly, we've got the P-flow jets instead of EM topo, which we'll be able to see later on how they've done with this. And again, the object-based met significance is used. So we've just seen the 2-step model, many jets, long cascade. They also have a few other signals scenarios they're looking for, which is this R parity violating. And the difference here is that the R parity violation allows there to be no stable SUSY particle in the final state. What we get is instead is a set of standard model quarks. And then there's also a GTT in which the gluinos can decay directly into these tops with the LSP production. And again, this has a similar signature, lots of jets with the met. Okay, I think it's worth noting actually how they calculate some of the backgrounds here, because it sort of contributes to what I'm going to say shortly. But the dominant background comes from this QCD multijet. So they have to use a fully data-driven method to estimate the background due to the fact that there's no Monte Carlo of sufficient stats and quality to simulate jets of 7 and above. But what they do instead is rely on this relative invariance of the met significance shape with changing n-jet. The idea is that as we can find the shape of the ETMIS significance and then scale it with n-jet with some relation. So this is obviously very important that this is calculated properly. So the actual shape itself is found a few jet multiplicities below the signal region in green here. So they'll calculate the shape for significance greater than 5, and then it can be normalized using these 2 regions, one at the lower multiplicity and then one at the higher at the signal region. And in this way, you can estimate the amount of QCD multijet contributing to the signal regions. Okay, and then just quickly to show you the exclusion plot that they've got. Again, in gray, we have the old limit for the 36 inverse femtobarns. And then with the red line, we have a multi-bin fit showing a really, really nice improvement in exclusion. But the main point I want to talk about is that this analysis also did a comparison between EM topo and P-flow. So we can see here on this one of their signal region plots, this is the significance distribution. And in yellow, we have this really large multi-jet contribution, especially at the lower significance. This is all QCD multi-jet, and then some other various backgrounds which are labeled here. But what they found was that the main background, the multi-jets, is reduced by 25 to 30% with P-flow. But not only that, the uncertainty related to it was reduced by 50%. And all of this translates to an improvement of about 30% in sensitivity, or 1 sigma, which is excellent. Okay, so just to conclude, using particle flow has demonstrably improved the sensitivity of this SUSY analysis that I showed you, the multi-jets. And as I've been the entire through theme, seeking this stable invisible particle benefits greatly from us reconstructing the ETMS better, and also telling if it's real or not. And this is the idea that any systematics limited analysis, you could make it stats limited, and that's the ideal scenario for these kinds of searches. And we looked at the new formulation of the MET and the significance and how it contributed. And finally, all of these advances are going to form the basis of Atlas Jets and ETMS physics for Run 3 and into the high Lumi era. So any questions?
Thanks a lot, Aaron, for this very nice talk. So yes, are there any questions or comments?
Excuse me, it's Mia. Can you hear me?
Yes.
Yeah, please go ahead.
I have actually 2 questions. The first one in slide 6. It's not clear to me how the track can affect the IETA in the plot on the right side. At pseudo rapidity 3 or 4, I see a slightly difference between the electromagnetic based and the particle flow one. But I guess at such a pseudo rapidity, the track acceptance does not cover. So which is the source of the improvement there?
Yeah, exactly. There is no, the track is going to end much before that. And I'm just trying to think what the reason for the improvement is. I think it's just a slightly better treatment of how we cluster the cells themselves in the forward region. So yes, the tracker doesn't contribute, but it's just a better treatment of the clustering.
Thanks. And another question, both in slide 24 and 19, where you show us the limit, current limit. It's not clear to me which is the impact of the increase in statistics and the one from the usage of the variable. Here, for instance, the significance. So.
Yeah, exactly. It can be difficult to see this. I know that especially in exotics, they had a sort of plot where they do scale it for just the increase in statistics, and then they have the 2 different versions, if you wish. So they have there's scaled with the previous analysis, and then the increased techniques. And I don't know if anybody's connected from the GT2 left on. I saw Federico was earlier, but if they did a study into this. I know there are plots available for the multi-jets analysis 24 that show that there is quite an impact from not just the stats, but those weren't made public.
Hi, can you hear me?
Yes, Federico.
Hi, it's Federico. Yeah, I'm connected, but for this analysis, we didn't disentangle the various improvements, so we don't have an official statement, or really can make a proper statement to say how much it's due just to the reoptimization due to the increased luminosity and how much is due to these new variables. While for the multi-jet, you had already in the talk some quantification of the improvement to that.
Yeah, exactly. Yeah, maybe that's perhaps something to think about for the SUSY group going forward. Maybe not necessarily copy the exotics, but do something similar, and then we can disentangle what we are improving with just stats and what we're improving with actual techniques. But at least we have the good improvement shown for. We don't have the public version of this plot, but there is a plot that shows the increase from EM topo, which sits quite a bit below and moving out.
Okay, thanks a lot. So are there more questions or comments? If not, we should move on. Thanks, Aaron.
No problem.
Yes, so Ashraf, maybe could you start sharing your slide? Yeah, perfect. Okay, so maybe full
Yeah,
screen, please.
I guess you can see them. So I will be talking about two analyses done in the CMS SUSY group. One of them is search for pair production of SUSY with final state of two opposite charge, same flavor leptons, and the other one is the opposite, two same sign or more leptons in the final state. The first analysis is opposite charge, same flavor leptons, and the signature is jets and missing transverse momentum combined with a dilepton. So the signal models considered in this analysis is all models that are preserving the R parity. And of course, the production is via SUSY pair production. There are 4 production modes, and there are quite a lot more Feynman diagrams, but here I listed the most significant 4 represents each category. So the production mode with a strong production, the first Feynman diagram, where the production is done via Goldwino, and this leads to 1 on-shell D in the final state. The second production mechanism is electroweak production, and this also has 1 on-shell D in the final state. The third one is direct S leptons, and this clearly has no on-shell D in the final state. And the last one is strong production with off-shell D, which we call edge. And I will be talking a bit about this edge. The signature is also, as I mentioned before, is opposite sign, same flavor lepton pair. And this always associated with jets, many or few, and missing transverse momentum. The analysis, as you can see, is covering a very wide range of final states and production mechanisms, but there is a common baseline selection applied to all the signal regions. And then each specific signal region has also its own criteria later on. The basic requirement is exactly for the search region, 2 opposite sign, same flavor leptons. And to build a control region corresponds to these signal regions, the flavor requirement is inverted. Then there are the mass of the dilepton system is built with the 2 leading leptons. And there are also some cleaning requirements, like requiring the boost of the Z candidate and reduce the cut, the delta phi cut that reduces the instrumental background from instrumental missing transverse momentum. So let me start with the standard model background. So the main background are 3 classes of background. So the flavor symmetric background, which is TT bar and WW, and also some other minor background. These are estimated from the different flavor side band, because we know that the ratio of a different flavor to same flavor yields in this background should be 1. But in fact, it deviates from 1 due to the trigger and reconstruction inefficiency. But for that, there are 2 correction factors accounting to actually invert the effect of these deviation. The second class of the background, which is Z plus nu, this is estimated from simulation. So the shapes are taken from simulation, and the normalization is taken from the multi-lepton control regions. And of course, for each search region, we build a different control region, and this control region is validated later on in a validation region corresponding to it. The last class of the background is the Drelian plus jets. This is actually should not have missing transverse momentum in the final state, but due to the jet miss measurement, it has instrumental missing transverse momentum. And this is estimated using gamma plus jets data as a proxy. And the shapes are weighted to match the kinematics of the Z plus jets for each signal region independently. And then it is normalized in the low mid region. And as you can see, there is a perfect agreement between the data Monte Carlo in the validation regions for the 2 backgrounds that are estimated from data. Next, so this is the edge signal, where we expect a no on-shell Z candidate, a combined reconstructed from the dilepton in the final state. And this signal can have many or few jets. So first, let me define the edge. So this is the next to lightest supersymmetric particle decays to the lightest supersymmetric particle and radiating 2 leptons at 2 different vertices. Because of the kinematic of these dilepton, when we reconstructed the invariant mass of this dilepton system, it forms a shape that is triangular, or we call edge. The main background for this analysis is TT bar, and for that we built a negative likelihood discriminator based on the kinematic observables, and this actually to discriminate that the events, whether they are TT-like or non-TT-like events. In order to gain sensitivity, there are 2 main search strategies are followed: the cut and count, the plot to the right. And actually, this is bend analysis based on the mass of the invariant mass and NBJet and the new discriminator, the negative likelihood TT bar discriminator. And you can see there is no significant deviation beyond the standard model prediction. And also the second search strategy, which is a simultaneous fit for the dilepton invariant mass. And for this also, there is no significant deviation beyond the standard model prediction. For this particular signal at invariant mass of dilepton 293, there is no significant deviation, either calculating the local or global significance. Coming to the interpretation for this analysis, so the first one I would like to mention is the S-lepton direct production interpretation. As I mentioned before, this is kind of have 2 opposite sign leptons with same flavor and no jet, but in fact there are a few jets can come from the initial state radiation and no on-shell D candidate in the final state. And you can see there are 2 plots for the most sensitive search region bends. And you can see the PT of the most sensitive 2, and there is no significant deviation for the data beyond the standard model prediction. And any fluctuation is actually within the uncertainty. This model excludes S-lepton masses up to 650 GeV. And then the next interpretation, the electroweak and the edge interpretation. For the electroweak, there is an on-shell D, and actually there are a couple more Feynman diagrams with the final state of ZZ or ZH. But this is the most significant one. And you can see the search actually is based on 15 search bends, based on the kinematical observables and also the kinematics of the associated W, whether it's boosted or not. And this final state actually exclude next lightest supersymmetric particle mass up to 750 GeV. The other interpretation is the edge, which I just described. This actually with a strong production, and as I mentioned before, cut and count and simultaneous fit of the dilepton mass fit search regions are used. And with both techniques, the exclusion of the S-bottom quark mass up to 1.4 TeV. Coming to the second analysis, this is a search for same sign leptons, and the final states are at least 2 jets. And then for the lepton requirement, there are 2 categories, either 2 same sign leptons, and the second category is 3 or more. And these actually final state are rarely produced by standard model background, as you already know, and the target models are either R parity conserving or R parity violating scenarios. And to gain sensitivity for this analysis, it's a multiple bin analysis, and actually the bins, it has search region with almost 160 search bins based on the kinematic observables. And here I put 2 control plots to show 2 of the important variables that you use in doing the binning, and you can see the data Monte Carlo agreement is quite perfect. So coming to the search strategy for this analysis, the background modeling is actually based on what we call event categorization. There are 6 signal categories based on the lepton PT and the lepton multiplicity. And then these categories are further split into based on the other kinematic observables. As you can see in the table and the two plots, for example, the SSHH category and then bend with other kinematic observables is SSHH stands for same sign dilepton. So this is a same sign dilepton search region, and HH because the dilepton are having high lepton PT. That means the first lepton is high and the second lepton is high. And the rest are actually following the same convention. And you can see these are the most two significant search regions. And in all of the bins, there is no significant deviation for the standard model, for the data beyond the standard model prediction. The background modeling for this analysis is done actually because we do have 3 background classes as well, the fake non-prompted sourced background. So these are actually background that kind of having a lepton from fake and non-prompted sources like TT bar and W plus jets. This is estimated from data-driven. And there are processes taken from simulation, and this the last class is charge flip, which is also taken from the data-driven. The interpretation for this analysis into both classes, the R parity violation Goluino pair production. It excludes Goluino masses up to 2.1 TeV for the 5-body decay, the plot to the far left. And the one in the middle, it excludes 1.7 TeV, and you can see also this is a 3-body decay for the Goluino. The second interpretation is the R parity conserving interpretation, where S bottom quark pair were pair produced, and this analysis excludes the S bottom quark in mass range between 0.9 and 1 TeV. There are more results in this context will be shown in Suham's talk later next to me, and also there are some interpretations in the backup. Coming to the conclusion, so I have presented a search for same sign or opposite sign or multi-lepton associated with jets and missing transverse momentum. And both analyses are concluded with no significant excess is found in the search region, and the limit on different SUSY particles are set in the context of each relevant SUSY model. The results are interpreted with several SUSY models, as I mentioned, considering R parity and R parity conserving and R parity violating scenarios. And in all of the results, the datasets used are full run-2 from 2016 to 18 datasets in order to exploit the many SUSY models with wide range of final and initial states. It is worth to mention that for both analyses, sophisticated analysis methods are mandatory to gain more sensitivity in general in SUSY searches, especially when we are targeting high mass regime. And there are still more yet to come in the pipeline. I think SUSY is extensively working in object tagging. So there are many analyses have been improved with object tagging, heavy or soft object tagging, including tau tagging, deep top or vector boson or scalar boson tagging. There are also some analysis in the pipeline that includes consider using the modern technique like deep neural network, and I think there are more yet to come. That's all from my side.
Thanks a lot. Very nice talk. So are there some urgent questions? It seems not. So in that case, we can move on. Thanks a lot.
Thanks.
Sorry?
Hi, do you hear me?
Yes.
Okay.
Yes.
Okay.
Yeah.
Let me share my screen.
So thanks a lot. So this is the last talk for the first session of today. So yes, our next speaker is Sohan Bhattacharya, who will be talking about the searching for supersymmetric partners of the top quarks at the CMS experiment. So please go ahead.
Sure. Hi, this is Soham here, and I'll be giving an overview of the searches for top quarks at the CMS experiment. So, so as you have seen this plot times before, the CMS recorded about 137 fem-to-1 inverse of high quality data in run 2. And using the data, several supersymmetric searches have been performed in a wide range of final states. Now, in this talk, I'll be focusing on the top squawk sector, which serves as a very important probe to a different variety of SUSY models and phase-space scenarios. So the top squawk searches are very important. For example, the tree-level Higgs mass receives large corrections involving top squawk loop, which you see in this diagram here. And hence, we need to understand the top sector very well in order to understand the stability of the Higgs mass. So the wide variety of searches can be broadly classified into different benchmark scenarios, which is shown in this lower diagram here. You can have purely BNO LSP scenarios where the top decays to B and chi10. You can have VNO NLSP where the top decays to chi10 via charge or a heavier neutralino. And then you can have Higgs-like scenarios. So these different scenarios involve different final states, and you need to optimize your searches to be sensitive to different scenarios. For example, in the BNO scenario, you will have tops, so you need top taggings for boosted tops. For the VNO NLSP scenarios, you need efficient B tagging to detect the B emitted from the stop going to B and charge. And for Higgs-like scenarios, you can have taus in the final state, so you need a good understanding of the taus in your detector. So in this talk, the searches that I'll be talking about, these focus on the BNO-like LSP and the VNO-like NLSP scenarios. And so the main searches here are the light stop pair production in dielectron and single lepton plus jets final states, and also a search of the heavier stop pair production or stop 2 pair production in the same sign leptons and multi-leptons plus jets final states. Okay, so coming to the first search, which is the stop 1 pair production in the dielectron final state using 137 fem-to-1 inverse of data. You see the search, the SMS or the same simplified mass spectrum models being explored by this search. You can have the stop decay into top and neutralino, or the stop can decay to a B and a chargino. And we consider we consider the top and the W bosons to decay to leptons in this search, because the leptons in the final state and the presence of significant amount of missing transverse energy, these help to reduce our standard model backgrounds. So the search strategy is the following. We require at least 2 oppositely charged leptons, electrons, or muons, and different cuts are applied to reduce different standard model backgrounds. I'll not go through all of them, but I'll mention one important one, which is what has changed with the previous iteration of the analysis, which is this S variable, which you also heard about in the talk before from Atlas. So this S is the PT miss significance. This is essentially a log likelihood ratio. And this reduces events where the detector effects and misreconstruction are the main sources of the missing energy. So using a cut on this S variable S greater than 12, one is able to more efficiently suppress events which do not contain any genuine missing energy. So following these baseline selections, the search region is binned into 12 bins based on the MT2 variable, the S variable, as shown in this table here. And now for the background estimation, TT bar is an important background. So events from top pair mostly populate the MT2 less than 100 GeV region, but the tails of MT2 can also be populated due to jet momentum resolution, mismeasurement of jet momentum. And for example, the electron or muon can fail the ID criteria we have, or the W can decay to taus, which can then decay to leptons instead of decaying to leptons directly. So these effects are checked in our control regions, which we define for this analysis, and we obtain a good closure between data and simulation, showing that we have good modeling of this effect. The genuine top pair background normalization is extracted from a signal depleted control region in the region MT2 less than 100, and correction factors for the other backgrounds are derived and applied to obtain a good closure. Here you see a few different variables, for example, the MT2 of the dielectron system, the MT2 of the B lepton system, and the S variable for background data and a couple of model points. And you see good, and you can see some separation power between our signal and the standard model background, showing the power of these search variables. Coming to the results, so the results for the 3 different SMS models searched here are shown here. First is a stop going to top neutralino, which is A. The second is stop going to B chargino, where the chargino decays to a W, and the third one is the stop going to B chargino, where the chargino decays to a slepton, which then decays to a lepton. So in each of these cases, A, B, and C, the stop mass is excluded up to 900, 800, and 1300 GeV respectively for a nearly massless LSP. Coming to the second final state of the lighter stop pair production, which is this search shown here with 137 Fem to 1 inverse of data. So even here, the SMS models that are considered, they are quite similar, except that the stop decaying to, except that the chargino to the slepton decay is not considered here. Here, one W boson decays to a lepton and the other decays to hadrons. Coming to the search strategy, for this we use missing energy, HT, and single lepton triggers, and require at least one isolated lepton, E or electron or muon. Then there's requirement of at least 2 jets and at least 1 BTAC jet, and some cut on the missing energy, MT, and a cut on the angle between the jet and the missing energy, which suppresses background from 2 leptonically decaying W bosons. So here in this search, the top can be quite boosted, and for that, the hadronic top can be quite boosted. So for that, a DNN-based top tagger is used to tag that, and there are 3 different tagging categories which are untagged, where the DNN tagger fails to tag. We have the resolved category where the 3 subjects are well resolved, and a merged category where the 3 subjects are very close to one another. And the third, and then the search region is divided into several bins in terms of the variables listed here. One important thing to mention here is the use of a soft B tagging, which is new in this iteration, where we tag Bs with very small PT above 1 GeV, and this is done by identifying a secondary vertex in the event that is not associated to jets or leptons. And this improves the sensitivity of this search in the compressed region, where the difference between the stop mass, where the mass difference is close to the W mass. And here you see the discriminants of the discriminant of the top tagging algorithms for the merged case and the resolved case here in the left and right, and you see a discrimination between signal and the background. The signal is shown in the dashed lines. The background estimation, there are 3 different major backgrounds here. One is the lost lepton background, where the events from 2 W bosons decaying leptonically, where one of the leptons is not reconstructed or identified. This is estimated using a dilepton data control sample. You can have, of course, the single lepton background, which is the genuine single lepton background. This is estimated using a data control sample which has no B jets in it. And then you can have the invisible background where the Z decays to a pair of neutrinos, so an event with a W and a Z boson. And this is estimated using simulation, and we obtain a good closure for these background estimations. And here in the bottom, you see 3 different search variables shown for the background and our signal in the dashed lines, and you see a good discrimination power offered by these variables in order to improve our sensitivity. Coming to the results, so even here you have the 3 different scenarios where the stop decays to top neutralino, which is type A. Type B is stop decaying to B and chargino, and type C is you can have a mixture of the 2, where one stop leg decays to top neutralino, the other leg decays to B chargino. And in these 3 cases, A, B, and C, the lighter stop mass is excluded up to 1200, 1150, and 1050 GeV respectively, for a nearly massless Chi-10. Okay, now this brings me to the last section of my talk, which is the heavier stop pair production in the same sign dilepton or multi-lepton plus jet final states. So here you have a stop 2 pair being produced, which decays to a Z and a stop 1, and then the stop 1 decays to top and neutralino. So the signature can contain 2 Higgs bosons, 2 Z bosons, or 1 of each, depending on how the stop 2 decays, whether to Z or Higgs. And 3 different branching fractions of the stop are considered. So the stop 2, stop 1 Z, this branching fraction can be 0%, 50%, or 100%. And you heard the details of the search strategy and the background estimation in our short stop, which was the last one. So I'll not be talking about these. So I'll go straight to the result of the search. The 3 different scenarios here mentioned are corresponding to the 3 different branching fractions, which I mentioned before. So the stop going to stop 1 Higgs 100% is the top left plot. The top right plot is where you have the mixed scenario where one stop goes to Z and the other stop to Higgs with a 50-50 probability. And the last one is where the stop 2 goes to stop 1 and Higgs with a 100% probability. And you see the mass exclusion in the 3 cases are 700, 750, and 900 GeV, 900 GeV respectively, with the largest mass exclusion being offered by the branching fraction to stop 1 and Z. So this brings me to my summary. I presented the recent results from different top score searches at CMS. And here is an overview of the different lists, the different stop quarks searches that have been performed at CMS in different final states, corresponding to the different benchmark scenarios, which I show here. So the Bino-like LSP, Bino-like NLSP, and the Higgs-like scenarios. So these scenarios, as I said before, they require a good understanding of a wide range of finite states involving leptons, jets, and taus, and we already have a very broad category of searches exploring each of these scenarios. And you can see a sort of a summary plot in the top left, which show the mass exclusions from a few general searches using HT, MIS, MT2, and a single lepton stop and a dilepton stop scenarios. And you can see that the hadronic or the 0 lepton scenarios, these offer the greatest exclusion. So we have an upcoming dedicated fully hadronic stop search, which we expect to give the largest sensitivity. And we also have a dedicated search of the top corridor, which you see here in this small gray region in this top left plot here. It is where the stop, where the difference between the stop and the LSC mass is close to the top mass. So we are dedicated search in this region of where you need special techniques. And we'll be having those results very soon. So the LHC is now in the long shutdown 2 and gearing for run 3. So stay tuned for more results. Thank you.
Thanks a lot for this very nice talk. So questions or comments? Perhaps this was all clear. Indeed, we have the coffee break after this talk. So maybe, yes, for any discussions or comments, we can iterate on Mattermost. Okay, so thanks a lot. So thank you. So we'll have a break. So we'll resume this session at 11. So, and then the speakers for the next block can test their shared screen and also audio during the break. So thank you everyone for joining this part of today.
Okay, so I'll be the chair for the next session. If you are speaking in the next session, I think we've already checked Cezanne Segman, but Thomas Stevenson, are you here?
Hi, yes, can you hear me?
Yes. Yep. Can you check your video and also share your slides so we can make sure it's working nicely?
Can you see this okay?
Yep.
Okay.
Are you full screen? Are you full screen or well? That's probably good enough. Anyway.
Do you still see it?
Can you advance? Yep, it's perfect. Can you advance? Yeah, perfect. That's all.
Okay,
great. Thank you. Next, Sarah Alderweireld.
Hello, let me share. Can you see this one? And is it changing?
Yes. Is it advancing? Yes, perfect. Thank you so much.
Thank
you. Yuri Fiaski.
Yeah, I'm here. I try to share my screen too. Okay, can you see it?
Yes, although we also see some addition. Okay, you're going full.
Yeah, like this should work, right? And I can change.
Yeah, sharing the slides on, but that's fine. There's nothing on top of it. Is your camera working as well, or are you?
Yeah. I think it is. I think you can see me now.
There you
okay.
go. Yeah.
All right.
Yeah, I'll ask you to use cameras unless you know you have.
Yeah, sure.
Problems with bandwidth, and then we better hear you than see you.
All right.
Okay. All right. Thank you very much. And it's Yuri or Judy? Sorry if I.
It's Yuri. That was correct pronunciation.
Yuri.
Yeah.
Perfect. Thank you. Let's see. Matthias may not be here yet, so let's go to.
Oh, actually,
oh, you're here, Matthias. Perfect.
I made it. Hi.
Hello. Yes, and
Hi.
this is the technical assistant of this session. I was informed that I will be sharing this presentation, so I'd like to.
Perfect.
Yep.
To make sure that everything is working the way it should be. And you see the picture?
Very nice. Thank you very much.
And the transition is
it's
fine.
advanced. Yep.
Great.
Very good.
Yep.
All right. So let's go to Frederick Hu.
Can you hear me?
Hi, yes.
So let's share the screen and like this.
Does it advance?
If I'm in the right window, probably.
There you go. Perfect. Thank you. All right, and then we have Miguel Crispin Romão.
Yeah, hi there. Let me share the
Hi.
screen then. Should be here. Should be able to see, and you should be able to see a red dot. Right.
All right. And does it advance? Yeah, perfect. Thank you, Miguel.
No worries.
And Xian Chen. Is she on here?
Yes. So let me share.
Yes.
Can you hear me?
Yes.
Okay.
Hi.
Cool. Let me file. Oh, sorry. I think I need to change one setting. So that would require me to reconnect actually. So.
All right. That's okay. We can
skip.
We can
one?
check. Yeah, we can check Darius, and then when we come back in, we can check you.
Oh yeah, perfect. Thank you.
All right. Darius Farouhi, are you here? Maybe we don't have Darius. Okay. So let's wait for Xian to reconnect.
Hello, I'm just back. So can I try that again? So, all right. Can you see the slide now?
Yes. Okay. Can you try to go full screen?
Sure. Does it look great too?
It looks good. And is it advancing?
Okay.
Can you go to the next one? Yeah. Yeah, it looks perfect.
Okay.
Cool. Thanks.
Thanks.
Very good. Thank you. All right. Please enjoy the next 6 minutes of break.
Thank you.
Okay, it's 11 a.m. So let's start on schedule. So I'm Alex Souza, and on behalf of my co-conveners Yu Nakahama, Nyatozi, and Michal Malinsky, will welcome you to the final portion of the VSM parallel sessions. I'll just like to reiterate to the speakers that all talks in this session are 12 minutes with 3 minutes for discussion, and so I'll give you a verbal reminder when you have 2 minutes left. And for the audience, please ask questions at the end of the talk using the Zoom raise hand feature, and of course, you can use the Mattermost as well. We'll be monitoring that. So in this session, we're going to be covering results from SUSY searches and techniques and algorithms, both for SUSY and geophysics searches. So hopefully it will be an exciting session. Our first talk here will be presented by Thomas Stevenson from the University of Sussex, and he's going to tell us about searches for direct pair production of stops and bottoms with the Atlas detector. So when you're ready, Thomas, please.
Let me just share my screen. Okay, can you see the slides okay?
Yep, perfect.
Okay, great, thank you. Thank you, yeah, I'm going to talk today about searches for direct pair production of stops and bottoms with the Atlas detector on behalf of the collaboration. So supersymmetry predicts the existence of a new family of partner particles, the standard model, which differ only by their spin. If natural supersymmetry exists, then it predicts that stop particles should have relatively small masses when compared to the other SUSY particles. And the cross sections to produce stops and bottoms would typically be larger than the electroweak partner particles. In this talk, I'm going to discuss searches for the third generation SUSY particles, so the bottom and the stop, in a bit of a whistle-stop tour. So far, both Atlas and CMS have excluded wide regions of the parameter space. So there's a need to search in the more challenging areas. So you can see in the top right plot, I've highlighted these areas, and I'll go through them in a second. These analyses can also have interpretations in dark matter models, as they have lead to similar final states. So there's strong evidence from astrophysical observations that dark matter should exist. However, the nature and the properties of the dark matter particles remain largely unknown still. Okay, so the first three analyses I'm going to go through, I've grouped together as they target similar regions, and these are the search for stop pairs in 0, 1, and 2 lepton final states. And so, as I say, they target similar regions and can be grouped together. So the diagram on the right shows these. So there's the 2-body decay region where you have a high mass stop pair produced. This leads to a large, and as you move back towards the 3-body decay region, a medium mass difference between the stop and the lightest neutralino. Then you have the 2/3-body region. So this yellow region, which is where the mass difference between the stop and the neutralino tends to be somewhere between the mass of the top quark and that of the W plus the B quark. And then, of course, there's the 4-body decay region, and this is where it's highly compressed and the mass difference approaches 0. And this is new for Atlas. And you can see on the left the corresponding Feynman diagrams for the different cases and the dark matter one as well. Okay, so the 0 and 1 lepton final states are shown here with the various techniques that are used to help discriminate between the backgrounds. So for the 2-body region, where you have these boosted stops, you can look for boosted top production. So this can either be done with top reconstruction variables or looking at reclustered small R jet finding, and there's the details of this linked here. The 3-body region uses things like the recursive jigsaw techniques, and then in the 4-body region, where you have these, the mass splitting is much smaller, you expect that B jets that are produced have relatively small PT, and so fail the normal jet reconstruction techniques. And as such, soft B tagging is used. Again, there's details linked here, but I think there's also a talk later in the session that will cover this in more detail. where you can go down to much smaller PT of about 5 GeV for these. Yes, for both the 0 and 1 lepton, the backgrounds are controlled and estimated using control and validation regions, with some of the major components coming from Z2 plus heavy flavor, jets, single top and TTZ production for the 0 lepton, and then also top pair production and TTV production and W plus jets production for the 1 lepton. The 2 lepton final state has similarly different signal regions targeting the 2, 3, and 4 body regions respectively. The selection is characterized by having exactly 2 opposite sign leptons with vetoes on low MLL for low mass resonances and also for on the Z mass window. And as Aaron mentioned in his talk earlier, the ET miss significance variable gives a significant improvement in sensitivity over the previous analyses. The signal region categories are further grouped into by number of jets and number of B-jets, as well as other variables. The major backgrounds again for this include TT bar production, TTZ, and diboson, as well as backgrounds from including fake and non-prompt leptons, referred to as FMP here. And these are estimated with dedicated control and validation regions, as also shown in these plots. Okay, so there's this nice summary plot that contains all 3 of these results here, and you can see the improvement here from the 0, particularly in this very compressed region, which comes from the use of soft B tagging, as well as the 1 lepton, and then also at this very high stop mass region, there's a good improvement from the TT bar, boosted TT bar reconstruction. And then you can also see that the 2 lepton improves this region here, where you start to approach the mass plane starts to approach the top mass. Also, the limits are set on the scalar and pseudoscalar mediator masses up to about 250 GeV for the dark matter interpretation. Okay, changing slightly to a different kind of search. This is a search for stop pairs in a Z and Higgs final states. So this is characterized by stops with a decay to a Higgs and a Z boson or 2 Z bosons, shown in the top Feynman diagrams. The 1 lepton analysis, which requires the Higgs, requires a Higgs candidate to B-jets, and the 3 lepton analysis is the one searching for the 2 Zs, and this requires same flavor opposite sign lepton pair in the Z window, as well as having its signal region based on the B-jets and leading jet PTs and other variables. The main background sources for this are TT bar plus heavy flavor and the TTZ production again, as well as diboson and hadrons, faking leptons, and faking leptons and non-prompt leptons being other relevant backgrounds. And again, the backgrounds are constrained via control regions in the fit. No significant excesses are seen again, and so limits are set. And you can see here both limits are on the stop neutralino 2 mass plane, as well as the stop 2 neutralino 1 mass plane. Okay, another search with Higgs in the decay process is the search for sputum pairs in final states of hadronic taus. So this is a model where you have the sputum decaying to a B and a neutralino 2, which then goes on to decay to a neutralino 1 via the emission of a Higgs. And one of these Higgs is required to decay to taus. It has a unique sensitivity compared to other Atlas analyses due to the requirement of these hadronically decaying taus that help to suppress the standard model background, but also the presence of the the associated tau neutrinos that add to the ET miss from the neutralino 1 allow you to probe the very low neutralino 2 masses, or the mass difference being very small. The signal region requires B-jets and hadronic taus, of course, and the key variable includes this min theta variable, which I'll show on the next slide as well. The largest background contributions comes from TT bar and single top processes, as well as, of course, Z tau tau plus jets. And again, the top and Z backgrounds are constrained using dedicated control regions. So for the signal region, there is this multi-bin signal region, as I say, defined in this min theta variable, which is the minimum angle between a tau and a B-jet, which is illustrated by this diagram here on the left. So it's the minimum one of the angle between any B and any tau. And it exploits the differences in the sources between the signal and the backgrounds, which are explained here. Again, no significant excesses are observed in the signal regions, and so limits are set in the bottom neutralino 2 mass plane here, as you can see. And you can see that it reaches this region here where the neutralino 2 mass is very, very small, or small compared to the reach of other analyses. Okay, for the final analysis, it's something a bit different. This is the search for new physics in final states with an energetic jet and large missing transverse momentum. So this is an inclusive signature sensitive to a wide range of new physics theories, including compressed SUSY and dark matter. And the idea is that the events are selected to have an energetic ISR jet and large missing ET, with up to 3 additional jets vetoing all other particles. The signal region is then divided into bins in the missing ET, and you search for an excess in this distribution. The dominant backgrounds here come from the Z nu plus jets and the WL nu plus jets, and top processes are also relevant, with control regions for the V plus jets processes and top processes. Again, no significant excesses are observed, so many different types of limits can be set, as I say, from this analysis, but in this case, I show ones related to the stop and the spottum. You can see here again that they're excluding masses up to around 520 GeV for the stop, for both the stop and the spottum. Again, it can also be interpreted in various different dark matter models, and I show one here on the right, for example, but there's more in the backup. So on slide 18, then it's just a summary. So there's the summary plot I already showed for the stop and the spottum, and then the various limits on the 3rd generation squark reduction. So to summarize, natural SUSY as an extension to the standard model is still eluding us. However, we're starting to search in more challenging areas of the phase space, or via more exotic decays with different final state signatures, requiring new and interesting analysis techniques, some of which will be covered in the talk later, including soft B tagging. And then I present here the limits from the various analyses. And just to conclude, on slide 20 is the links to related talks on both the reconstruction techniques and other SUSY searches. Thank you.
All right, thanks very much, Thomas, for these very nice results. Are there questions? I don't see any questions.
Excuse me.
Yeah.
Can you hear me?
Yeah. Yeah, absolutely.
A quick question. I'm sorry if I missed this comment. In slide number 11, on the plot, the limit plot on the right side has this kind of S shape.
Yes.
Which is kind of unintuitive for me. Can you comment a little bit more?
Sure. So on this plot here, there's the 2 Z regions, signal regions, which are respectively sensitive. Some are sensitive to this side of the plot here, where you have the large stop 2 mass, whereas the other signal region is sensitive more to where the mass splitting between the 2 is between the stop 2 and the stop 1 is approaching the Z mass. So the 2 sections are essentially dominated by 2 separate signal regions, and that's why in between you sort of have less sensitivity, because they're optimized more for those 2 regions.
Actually, I had a question on slide 13. You mentioned that the missing energy is what gives you unique sensitivity, the missing energy because of tau neutrinos. So I assume the systematics on that determines, or how well you can reconstruct that missing energy determines the sensitivity of this analysis. Maybe.
I'm not entirely sure, but the systematic sources main systematic sources are listed in the backup. So
okay.
I would imagine that it is somewhat a limiting factor.
Okay, I was just wondering, you know, since it's probably one of the difficulties of this analysis, if there are any plans on how to improve it further, this aspect of it, either through reconstruction improvements or other methods. Okay. Any other questions? All right. If not, thanks very much, Thomas, again. And we'll go to the next talk. So our next speaker is Sezen Sekman from Kyung Pok National University, and he'll be telling us how to dig deeper into the SUSY parameter space using CMS.
Hello, can you hear me?
Yes.
Okay. Thank you very much. So I'll be telling about how we are using non-standard searches to dig deeper into SUSY parameter space with the CMS experiment. So we have a lot of classical SUSY searches, and they've not yet provided an evidence for SUSY. Examples of these searches are inclusive searches with a lot of different search regions, stop searches, which we've heard in Sohan's talk, or leptonic searches, which we've heard in Ashraf's talk recently. But this is not an issue because SUSY can still be hidden in distant or unique corners of the SUSY parameter space. And we're designing a lot of new searches, dedicated searches to explore these corners. For example, for the cases with compressed mass spectra, we have searches with soft objects plus ISR jets, or searches that use long-lived particles. Or for cases with high masses or high mass differences, we have searches with boosted objects. And for models with accessible leptons or staus, we have dedicated searches. Then for cases with Higgs in the cascades, we have searches with reconstructed Higgs bosons. Or for signatures with specific combinations of objects, we have searches looking for these combinations, such as those looking at gamma plus B or gamma plus lepton. And last but not least, for RPV models, we have searches with low missing transverse energy or with high multiplicity. So there are a lot of examples. And in this talk, I'm going to present 3 recent non-classic search examples from CMS. So I start with a search for boosted ZZ plus missing transverse momentum. So here we are targeting gluino decays that cascade via a massive, relatively massive neutralino 2 to a light neutralino 1. So these are motivated by natural SUSY. So in this case, we have a small gluino neutralino 2 mass difference and a large neutralino 2 neutralino 1 mass difference, which is leading to two highly boosted Z bosons and the PT-miss signature. So to select the signature, we're asking for no leptons, at least 2 Z candidates, at least 2 jets, a PT-miss of 300 GeV and a hadronic transverse mass of at least 400 GeV. Then we select Z candidates from large radius AK8 jets with momentum at least 200 and the mass between 40 and 140. And the angular separation between the second highest PT-Z boson and any B-jet event in the event should be at least 0.8. So we have our signal selection, and the main background in the selection comes from Z to invisible plus jets. And we use control regions to estimate these backgrounds. And the control regions are defined from Z mass sidebands. So first of all, we estimate the overall normalized background by looking at the mass sideband of the hardest Z-jet, the first Z-jet. And we do a fit to the AK jet mass distribution, as we see in the figure there, to estimate the integrated normalized background. Then we get the PT-miss shape from a control region, which is defined from the sidebands of both Z-jets, assuming that the jet mass and the PT-miss have minimal correlation there. So as a result, we search for an excess in PT misspins and we find none, as we see in the figure on the left here. Then we interpret using a model, a Gluino model with a Gluino-neutralino mass difference fixed to 50 GeV and a neutralino-1 mass fixed to 1 GeV. So we have Gluino decays to low momentum quark pair and neutralino-2 decays to boosted Z's plus a neutralino-1. In this model, as we see in the plot, we are able to exclude Gluinos up to 1.9 TeV. So the next search is a search for compressed SUSY with soft taus. So here we are considering staus with a low stau neutralino-1 mass difference of at most 50 GeV. And such cases are usually favored by dark matter co-annihilation scenarios. So this analysis looking at either the direct production of electroweak gauge-inos or staus. So staus can come from the electroweak gauge-ino decays. And the final state has a soft hadronic tau plus an ISR jet plus missing transverse momentum. And it's the first search with this signature. So the selection here consists of a tau with a PT between 20 and 40 GeV, an ISR jet with a PT of at least 100, and missing ET of at least 230. Then the angular separation between the jet and missing ET should be greater than 0.7. And in order to get rid of TT jets, we ask for 0 B jets here. And we're looking for an excess in the tau transverse mass distribution. So the backgrounds are estimated here using control regions again for TT jets and W jets backgrounds. We use the MT shape from control regions and extrapolate yields using Monte Carlo. Then QCD background, we estimate completely from data, again, get the MT shape and yields from data control regions. So we can see the overall result in this plot here. And unfortunately, again, we see no excess. So we do an interpretation based on 2 models. So one is the electroweak gauge-ino model, neutralino-2, chargino-1 or chargino-1 pair production. So for the case of 100% Vino, neutralino or chargino, for a mass difference smaller than 50 GeV, we're able to exclude neutralinos or charginos less than 290 GeV. And this is the most stringent limit up to now, and it's the first study to surpass the LEP exclusion limit of 103.5 GeV for compressed scenarios, of course. And we also look at stau pair production. Here we get no sensitivity yet. The plot shows the observed limit over theory limit ratio, and the best we can go there is about 12 for low stau and neutralino masses. Okay, this brings me to the last search, which is a search for disappearing tracks using the MT2 variable. So again, here we're looking at compressed SUSY cases with chargino-neutralino mass difference very small, about 100 MeV this time. And this makes chargino to be long-lived. And here the chargino decays inside the tracker to a soft, undetectable pion and missing ET. And this gives us a disappearing track signature. So CMS already had, for a long time, the inclusive hadronic search based on the MT2 kinematic variable. And this search has been recently extended by adding disappearing track signatures and at least 2 jets and an MT2 greater than 200 GeV search regions. And so it could look for compressed chargino in Gluino quark decays. So for the disappearing track selection, we have a categorization. So we categorize tracks into short tracks, which are pixel only, or medium or long tracks, which are reconstructed in pixel and strip detectors of CMS. And this allows us to search for a range of different lifetimes. Then the disappearing track requirement very nicely allowed to go lower in several kinematic requirements. For example, MT2 was reduced from 400 in inclusive to 200 in disappearing track search. We have search winds in this analysis that are defined by a number of jets, HT, or disappearing track length, or disappearing track PT. So we have 86 of these search regions. So here, backgrounds consist of either hadrons or leptons that are poorly reconstructed in the tracker, or tracks that are built out of incorrect, random incorrect combination of hits. And to estimate these backgrounds, we calculate fake rate in various data control regions and apply these fake rates to disappearing track candidates in the signal regions. So this search led to a serious improvement in our limits. So the effect of extending can be seen in this slide and the next one. The plots on the left are giving limits from the inclusive search, whereas the ones, corresponding ones on the right are extending the search with disappearing track. So as we can see, I'm not going to read all the numbers, but there are, in all cases, several hundred GeV extensions to the limit, especially in the compressed region where we have the mother particle, let's say gluino or squark mass, very close to the neutralino mass, which we see at the upper left corner. So the previous page was for squarks and gluinos, and this page is showing the limits for stops. Again, we see a serious improvement, especially in the neutralino mass reach, which is taking us up by about 700 GeV. And here I also show limits, where we take one mass value, of 1 TeV for stop, and the limits are shown here for Chargino mass or sigma over sigma theory as function of Chargino proper decay length. Okay, so these were the recent searches, but CMS also has many other searches looking at non-standard signatures, and here's a list of these. These are a little bit earlier. So we have searches for BJets and photons, 6 gamma gamma, other STAU searches, other searches involving boosted objects, VBF, RPV, etc., etc. Okay. So to summarize, we have not found SUSY in classical inclusive stop or leptonic SUSY searches, but we are supplementing these searches increasingly by dedicated searches for specific scenarios or exclusive signatures. So I presented 3 searches, like a boosted ZZ plus MET search, which extended the gluino mass reach to 1.9 GeV. For low gluino neutralino 2 mass differences. And then the second one was a soft tau plus MET plus ISR jet search for compressed STAUs, which are dedicated by dark matter scenarios. And this search was able to obtain the best sensitivity for Charginos in the compressed range and surpassed the LEP limit. And finally, the disappearing track search, while adding search regions with disappearing tracks to the inclusive hadronic MT2 search significantly increased the gluino squark stop mass limits, about 400 to 600 GeV, and indeed very significantly improved sensitivity in the compressed region. So yeah, these were the searches, but this is not all. We have other dedicated searches from the past and others that are on the way to explore SUSY further. So 2 searches that will be upcoming are soft opposite sign to lepton search and the very interesting machine learning based search on stealth and RPV stops. Thank you.
Okay, thank you very much for, again, these very nice results. So we do have time for questions. Are there any questions for the speaker? What's the time scale for this R parity violation? Stops.
Peter, are you still there? maybe you could answer. Yeah, this search has been there for a long time at the
A few months. I mean, let's put it like that. That's at the order of 1-2 months. I would say 2 months. Let's say.
Oh, that's good. That's exciting.
That's a very interesting one indeed.
Yes. All right. Let me check Mattermost. I don't see questions there, but feel free to use Mattermost to ask questions that didn't occur to you right now. I don't see any other questions. So thank you very much again.
Thank you.
Let's go to the next talk. The speaker will be Sarah Alderweireld from CERN, and will be telling us about searches for the electroweak production of supersymmetric particles with ATLAS.
Okay, I think you can see my slides. So indeed, I will tell you a bit more about the ATLAS searches for electroweak supersymmetry. Repeating quickly why we look for electroweak supersymmetry, as illustrated on the bottom left figure, we know that the exclusion on strong SUSY production is now reaching well beyond the TeV scale, while our constraints on electroweak SUSY are currently still weaker. And as the broad exclusions put pressure on natural SUSY going forward, the electroweak searches are continually important at LHC. So when using the full run-2 data set, we aim to keep pushing the exclusion limits if we can't find SUSY, but we must also make sure to cover gaps in challenging regions, which is illustrated, for example, by the compressed Higgs search that was published late last year. So in terms of the current spectrum of ATLAS searches, we are separating these by production mode, intermediate states and final states. So starting with electroweak paired production, we've got the ones considering intermediate boson decays, as well as intermediate lepton decays, and then have a wide range of results for different final states. On the other hand, for the direct lepton production, here we have this exclusion driven by the 2-lepton result, but also different ones are available. Given the short talk today, I will focus on a couple of these only, the most recent 3-lepton and 4 or more lepton results, and additionally talk about 2 RPV interpretations in these final states. Starting with our new result for 4 or more leptons, this search considers up to 2 hadronic taus within the 4 or more leptons. And these high lepton multiplicities provide good handles for background rejection. In the summary plot, you can see the dominant background contributions from diboson or TTZ production, as well as from misidentified leptons. And regions to search are created by the presence or absence of Z bosons, and then further separating by hadronic tau or B-jet multiplicity, as well as missing transverse energy and effective mass. The interpretation is done in 2 ways. On the R-parity conserving side, we use the general gauge mediation model, considering a light mass degenerate Higgs triplet, with then paired production considered somewhat inclusively, and decays to a nearly massless Gravitino LSP, as well as then the multi-lepton final state. On the RPV side, which was also discussed by Johannes on Tuesday, production is considered with all of 3 Winos, lepton, and gluino NLSP scenarios. And in all of the cases, then RPV decays of the neutralino to lepton-lepton neutrino is considered. And the analysis specifically targets the extremes of the coupling in tau multiplicity, so tau enhanced or tau depleted. And looking again at the summary plot, we see overall a nice agreement with the standard model. And then the first few regions using the Z presence target the RPC interpretation, while the middle set of regions targets the RPV interpretations. And notice also on the right, the 5 or more light lepton general search region, which was added to the set. On the RPC side, for the search regions, we can see that the analysis makes use of intermediate and slightly tighter MET selections, as well as a B veto to discriminate. and also regions without ZB veto are included to follow up on an excess from the previous incarnation of the analysis. Looking then at the exclusion this provides, given high branching ratio from Z to leptons, the sensitivity is best at high branching to Z plus gravitino, which given the axis is here at the low values. And then you can see it dropping off slightly as you go to more branching to Higgs plus gravitino. This result is also nicely compatible with the previous 4B result, which has more sensitivity at higher branching to Higgs plus gravitino. Again, on the RPV side then, here we move to the selection using the Z veto and separating again by B multiplicity. Here, if we look at the M effective distributions, we find more general search regions or validation regions at intermediate values of M effective, while the search regions specifically targeting the different coupling extremes are situated at very high M effective. In terms of exclusion, here we showed results for the Reno NLSP scenario. We find that for the tau depleted case, the limit is set at 1.6 TeV, and for the tau enhanced coupling, slightly lower at 1.15 TeV. Moving then to the RPV Chargino interpretation of the trilepton search, this analysis searches for resonance in the trilepton invariant mass. This means we look at pair production of Chargino-neutralino or Chargino-Chargino, and then request at least one leg to have the RPV decay of the sparticle to boson plus lepton or neutrino, while the second leg can be different. The events are assigned into 3 search regions, either 3-lepton or 4-lepton or fully reconstructed, depending on the presence of more leptons or more reconstructed legs. If both legs are then reconstructed, you can see that the mass asymmetry variable between the 2 legs, shown on the top left, has the signals peaking at much lower values than the background, so that's nice for discrimination. Further discrimination also in typical values like the missing transverse energy and the MT. And then more specifically, the analysis bins the results in the MZL mass variable, where you can see the peak of the different signals at different mass values. And a simultaneous fit then allows us to capture the different contributions very nicely. The analysis was also discussed in an Atlas physics briefing, which you can find at the link on the bottom left. Again, from the summary plot, we see also no large deviations from the standard model. So that brings us to further interpretation, which is done in terms of branching fraction to bosons and leptons. 4 scenarios for the lepton branching fraction are considered, either equally to each of the lepton types or individually with 100% to the specific lepton. Then the results are presented as a scan of the branching fraction to bosons on the y-axis, here branching fraction to Z, because as this targets the 3-lepton resonance specifically, the sensitivity is dominated by this branching fraction to Z bosons. And I show the figures for the inclusive or tau lepton interpretations. The electron and mu cases are in the backup, but you can see then the exclusion largest at high branching fraction to Z and dropping off, especially when the branching fraction goes below 20%. Then moving to the 3-lepton result, here we consider Chargino-neutralino pair production, decaying to 3 leptons, but specifically intermediate states using W and Z bosons or W and H bosons, and making the interpretation with Reno NLSP. There are 2 selections. Then first, on the on-shell WZ side and the WH side, the target is the phase space with mass splittings near the Z mass, which is specifically challenging in the gap between the compressed and the bulk region. and then also trying to push slightly to higher NLSP values, while the off-shell selection uses the targets the low, more compressed region of this phase space. Looking at the summary plots on the right, you see the multitude of regions and the dominant background being WZ and TT bar production, and in the off-shell case also quite some misidentified leptons. And again, overall fairly nice agreement with the standard model. Zooming in a bit on the selections, the on-shell and WH selection separates events picking same flavor opposite sign lepton pairs and reconstructing the dilepton invariant mass, then looking on the Z peak for the on-shell WZ regions and below or above targeting the WH. In the figures on the left, you can then also appreciate the difference in shape in the missing transverse energy and MT variables of the background signals with mass splittings near the Z mass or at higher mass splittings. And the analysis makes use of these shapes to target the different mass splittings by binning in these variables, as well as in jet multiplicity and taking HT into account.
You have 2 minutes left, sir.
On top of the already large number of same flavor opposite sign regions, we also add 2 different flavor opposite sign regions targeting specifically the WH selection, where the nearness of the decay of the leptons in the Higgs decay is used as an additional discriminating variable. Then in parallel on the off-shell side, same type of same flavor opposite sign events, but then targeting the dilepton mass below the Z peak and separating events again by ET miss and jet multiplicity. But additionally, the signal provides kinematic endpoints in both the MLL min variable as well as the transverse mass. And so the analysis slices in this variable to target each of the signals more optimally. And also selection on other discriminating variables is optimized per slice in these variables. Interesting also is the additional acceptance that is obtained for soft leptons targeting the most compressed areas of the phase space by adding ET miss triggers for the high MET selection on top of the commonly used lepton triggers. And the last addition would be the BDT-based isolation, which is also discussed in Shion's talk later in the session, which helps to reduce the fake lepton background, which is quite prominent in these selections. In terms of exclusion this provides, we can first look at the W and Z intermediate states, where for the bulk region, we see a very nice improvement near the Z mass, compared here in pale gray to the run 1 result, but also improving over the early run 2 result in 2 or 3 lepton final states. And then moving to the intermediate compressed and more compressed region, the off-shell selection again pushes the exclusion and matches nicely with the result in dark gray, which is from the full run 2 compressed search published late last year. Added on this figure is also the observed relic density interpretation following this paper, with then over and under abundant regions above and below the blue line. On the side of the WH intermediate states, we find exclusions up to 185 GeV for small LSP masses, which is about a 30 GeV improvement over previous results. So I've highlighted the 3 most recent results from Atlas Electroweak side, but please don't forget that we've got several more, which I did not have time to discuss today. I provide here the links, and if you have any questions, don't hesitate to ask. And also stay tuned for more results.
Thank you very much for this very nice talk. Okay, so we do have time for questions here. Any questions? Let me check Mattermost. Okay, that's it. Let's talk. All right, I don't see any questions at this point. So again, if they occur to you, please go to Mattermost, and hopefully Sarah can reply to them there. So thank you very much, Sarah. And let's go to the next one. The next talk is from Yuri Fiaski from University of Münster. Will be telling us about resummation effects in weak SUSY processes.
Okay, thank you. I think you can see my presentation.
Yeah, if you can get rid of the list. Yeah, there you go.
Yes, okay. Okay. So thank you for opportunity of presenting our work. So we have seen in the previous talks impressive updates and improvements from the experimental analysis. I will show here some small improvement from the theoretical side. In particular, I will discuss resummation effects in weak SUSY processes. These are the topics of the talk. I will just introduce very quickly for time, due to time constraints, some feature of resummation, and then I will go through our results for cross-section updated cross-section calculation at approximate next to leading order plus next to leading log. That I will explain later exactly what which ingredients fall into this definition. For lepton pair production and for electroweak pair production in the two configuration of mostly Higgs-Zenos and mostly gay-Zenos. Okay, just very quickly introduce about resummation. You know that in the perturbative expansion at every order, there are some logarithmic terms that appear, which can be large in some kinematical regions, namely when heavy particles are produced at threshold or with small transverse momentum. And these large logarithms, they can spoil the convergence of the perturbative expansion. So a resummation to all orders of these large logarithms is in order. And these can be done through some techniques that have been developed in the past, which involve transformation of the cross-section into Mellin space. All the results that I will show in the future, they have been obtained using the Resumino package, where we have included the latest, all the latest results. When we switch to Mellin space, these large logarithm, they are translated into these large values of this parameter n. And the cross-section is factorized into two pieces. One represents the hard function, which is independent of this n, but is process-dependent. And another part which can be exponentiated, which depends on this parameter n, but it is universal. It means that it depends only on the initial state, basically. And this can be, this exponent can be further expanded into various terms in powers of alpha strong, and each term of its expansion represents one power of the log of the logarithm that we want to resum. So if in this case, in our work, we have included next to leading log resummation, which means that we have included this G3 term. In order to include this term, there are a lot of ingredients that are necessary. You can find them in the literature. Here are just some of them. And again, also another ingredient that we need are the cross-section at next to leading order. These can be found in the literature, and by means of the hard matching coefficients, which are calculated from the ratio of the fixed order cross-section in Mellin space over the leading order cross-section, the Born cross-section in Mellin space. The results are shown here again. And finally, the last step, it will be to do the matching between the resummed results and the fixed order results, because we know that they are valid in two different kinematical regions, so we have to match them together by subtracting their overlap. Again, here are a last set of equations that show the exact formulas that we need with the precise at the specific order in the perturbative expansion. We are working at order alpha strong squared, which means a next to leading order. However, in the following results, the SUSY QCD correction are not considered at next to leading order, but only at next to leading order. This is why we have denoted these results as approximate next to leading order, which means that we only have standard model next to leading order correction. However, we would expect that SUSY QCD corrections are subdominant because the particles that enter in the loops are squark and gluinos, and they are heavy. Finally, the last step will be to perform an inverse Mellin transformation to come back to the original physical space. Okay, let me go through the results. We will just comment on Zlepton per production. I will not comment too much on the experimental part, which has been already covered in the previous plots. I also apologize that the CMS plot is not really updated with the latest one. However, now I've seen that the limits for Zleptons are the same for CMS and Atlas, and they reach about 700 GeV. Of course, with a strong dependence on the neutrino mass in the compressed spectrum. Here we show our results for the invariant mass distribution of Zlepton per production, where we have fixed the mass of the Zleptons at 1 TeV. On the left plot, you can see the differential cross-section, and in the bottom, the K factor. So we have all these curves, the leading order, next to leading order, next to leading order plus next to leading log, and the new results, which is an approximate next to leading order plus next to leading log. From the K factor in the bottom, you can see that basically the increase from next to leading order plus next to leading log to the new result is about 1%. So the difference is not large, but we know that one of the main benefits of resummation is actually to improve a lot the scale uncertainty of our results. So this is shown in the plot on the right, where you can see the error bands for the results at next to leading order plus next to leading log compared to the new result. And you can see that the error bands reduces visibly from about 1% to 1 per mil. So we have about 1 per mil uncertainty, scale uncertainty now. This instead is the result for the total cross-section that we have scanned for Zlepton masses going from 700 GeV, which is the exclusion limit, up to 1.5 TeV. Again, you can see the K factor in the panel plot on the left, and the increase now the new corrections is about 1 to 2%. Again, the most remarkable feature is the improvement in the scale uncertainty that you can see in the plot on the right, which goes from few percent now to 0.1%. So again, to the per mil level. We also have studied the dependence of the cross-section on the gluino and squark masses that you can see in the plots on the left. In this contour plot, we have the masses of the SUSY particles in the axis, and the color scheme shows which is the K factor between next to leading order and leading order cross-section. This is just to show that the K factor actually varies less than 2% by varying the masses of the SUSY particles. So the dependence on these masses is quite weak. And similarly, is also very weak the dependence on the A0 parameters, which determines actually the mixing, this bottom mixing. Okay, again, the cross-section just changes of less than 1% in general. Now we move to the electrowikino results. Again, electrowikinos can be theoretically, they can be generated in two different configurations. They can be either mostly Higgs-inos or mostly gauge-inos, and depending on which configuration once one wants to study, there are different signatures that could be considered. Again, I'm showing here the experimental exclusion limits from Atlas and CMS. The CMS one are updated, and again, they give similar exclusion limits as Atlas. And we can state that the Chargino's masses are excluded below 450 GeV. So, and for in the mostly Gaugino case, instead the limits are much stronger, and they exclude Chargino masses below 1 TeV. For the purpose of our study, we have implemented these two scenarios using following the indication that were already presented in this paper. So basically, by choosing appropriate input parameters that you can see here, one can obtain spectra which are either mostly Higgsino or mostly Gaugino in more than 98% component. I show first the results for Higgsinos. For the Higgsino case, again, first the invariant mass distribution. Again, you can see the K factors in the left, and the improvement, the correction of the new results, they give about plus or minus 2% correction to the total, to the invariant, to the differential cross section. And again, we can see an improvement in the scale uncertainty of the results of about some per mil.
You have 2 minutes left.
Okay, thank you. Here are the results instead for a total cross section in the mostly Higgsino case, very similarly to the previous plot as before. Now we can see that the corrections of the new results are about 5% for, especially for, and they are larger for low Higgsino masses. So these corrections are actually important. And again, on the right, you can see a visible reduction of the scale uncertainty from some percent to actually below percent. So again, a good improvement of the stability of the results. Similarly to before, we also studied the dependence on gluino and squark masses. Again, the dependence is very, very weak. We have this K factor that varies about 1 per mil, and also the dependence on the A0 parameters is again very weak, so not much dependence on this bottom mixing. For the mostly Gaugino case, since these particles are much heavier, we are scanning, here we are considering electrowikino masses of about 1.5 TeV. We have actually a very large contribution from T and U channel, which actually cancel largely the squared of the S channel contribution and their interference term. So actually there are some cancellation that occur in this case, and this actually translates mostly in a bit smaller reduction of the scale uncertainty that you can see in the plots on the right. So instead of the nice scale uncertainty reduction that we saw before, now it is the scale uncertainty is just slightly reduced. And similarly, it happens for the total cross section. Again, you can see the K factors are about 4% to the previous results. So again, quite some important contribution, but in the scale uncertainty in the plots on the right is visibly reduced for light Higgsinos, but is not as small, is not, the reduction is less visible, let's say, at, for heavier Gauginos. Again, we have studied the dependence on the gluino squark masses. Here, the dependence is much stronger, and this result is basically due to the fact that we have some on-shell production of intermediate squark in the final state. And this resonant contribution actually produces a very large contribution from the K factors, which means that actually one really have to consider next leading order cross-section. While the dependence on the A0 parameters instead remains pretty small. I arrive to my conclusion that we just leave it here because I think I am already running out of time. So just we can go through them if you have questions. Thank you.
Thank you. Thank you very much for all this work in improving these uncertainties. I think it's much appreciated. Are there questions for you?
I would have one. It's Michal.
Go ahead.
Hi, Michal.
This is extremely impressive, really. Like, I would like to ask you how far you can actually, or how far you expect you can actually push this program of like calculating higher and higher orders, and what are the main challenges in this?
So already next to leading order has been quite challenging in the sense that so we have mainly used some results that were already in the literature. So as far as we are just translating those results into the code, that's not a big deal. However, from the theoretical point of view, one will need to compute these cross sections at a higher and higher order in the perturbative expansion, and that starts to become more difficult. From the implementation point of view, the difficulties are relatively small, let's say. It's more, I think, from the calculation, point of view.
Yeah. Okay, thank you.
I had actually one question on a clarification, maybe on slide 12, I believe. Yes, or slide 11. The reduction of scale uncertainties you mentioned here, that you go to 1 per mil. This is for first and second generations.
Yes, yes. I mean,
well, do you have anything to say for third generation?
The thing is, so from the theoretical point of view, nothing changes between the 3 generations. What changes is only from it's only from the experimental perspective, right? Because third generation they are decaying into taus that again they will require some their specific analysis. So you have some efficiencies and some branching ratios to take into account. So the limits are a little bit weaker for third generation, but from the theoretical point of view, the calculations are exactly the same.
So it applies exactly the same way.
Yeah,
okay.
I mean, in the sense that you can have some modulation in the sense that, taus can mix. So you can have a bit slightly different cross-section for purely right-handed, left-handed, or mixed. But this is just a modulation of the cross-section.
Okay, very good. Any final questions before we move on? Let me quickly check Mattermost. No. Okay. Thank you very much, Yuri.
Thank you.
It's very good talk. Yeah. All right. So our next talk will be shared by the host, please, and it will be by Matthias Schott from University of Mainz on reinterpreting fiducial cross-section measurements in view of new physics being present.
Okay.
Matthias.
I hope you can hear me well.
Yep.
So let's start
well.
with the second slide to give you a brief introduction of what this presentation is about. So obviously, if you're a theoretician which has a new model prediction and you want to test your model, essentially you have 4 options. What you could do, the first thing is, and obviously what we as experimental physicists like the most, is you just come to us and ask Fidelity Corporations to do this model study for you and put places limits on your model or even discover that. Second option, which came a little bit more into action in the recent years, is just using the LHC open data, for example, from CMS to do your own data analysis. However, if you want to do this, you will realize that this is actually far from trivial, because essentially you need some experimental knowledge to do so. The third option is you use the published reconstructed data plots, for example, what you see on the lower right side, and then try to read off these dots and then place a limit on your model using this reconstruction level data. However, the problem here is that you essentially need a detector simulation for your signal and do this. And the fourth option is just use detector corrected or unfolded data. And this actually became quite modern in the recent years. The problem is that there's a model bias. And what came up in many discussions in the previous years on this fourth option is how big actually this model bias is. So let's go to the next slide and just see how this translates in a real physical problem. So you have to understand that each measurement which we put out at the LHC is typically assuming the standard model when it removes detector effects. So what does this mean is, so let's assume this, we want to measure fiducial cross-section, which is a typical cross-section measurement. This is this very simple formula here. So you have the number of candidate events minus the number of background events. And then you divide this by the integrated luminosity and this C factor, which in some sense just corrects for your detector. And a very simple definition of the C factor is just given here. You just look how many Monte Carlo events you have on detector level, so reconstructed, divided by the number of Monte Carlo events that you have at particle level. Now, important is that the C factor is typically derived, or can be only derived, assuming one specific process, and there typically you take a standard model process. Now, this is, and that's actually where this model dependence comes in, right, in the C factor definition. Now, if you want to go a little bit more complicated and go for differential cross-sections, well, actually, this is, in the end, it reduces it in some sense always to this formula, because also unfolding can be reinterpreted to the first order as a bin-by-bin unfolding, and this is essentially nothing else than a fiducial cross-section measurement, as you see here. So let's just go for a very quick example that you see the problem. Let's assume you have 800 observed events for a given process X in the standard model, and you have 100 inverse picobarn as data set, and you have a C factor of 0.8, which you estimate by Monte Carlo. Then your measured cross-section is 10 picobarn, and then this you compare with the standard model prediction, which is 8 picobarn. And then the question is clearly, can you place a limit on a model Y, a BSM model Y, using these two numbers? So when the C factor is the same for your model, for your process X in the standard model and the process Y in BSM, then you just say, well, a 95 confidence limit is something like 2 inverse picobarn, like twice, 2 times 2 picobarn. The problem is now that you typically do not know the C factor C, and just assume it's very different from the standard model, then you will easily get also factors of an uncertainty in your results. Okay, that's a basic problem. And if you go to the next slide, this already introduces now the idea of the study. So what we wanted to do is we wanted to estimate actually how big this uncertainty really is in practice. Because typically you hear in these discussions, oh, there's a model bias, you shouldn't do this. But obviously what's much more important is how big is this bias. So what the basic idea is now here, we simulated many standard model processes and BSM processes and look at many different possible fiducial phase spaces and then just sample over those and look at the variation of the C factor. That's the basic idea of the study. So we looked at 8 standard model processes, 4 EFT scenarios, and 6 BSM scenarios, where we tested 3 to 4 different model parameters for each of these BSM scenarios, which we had in mind. Now let's go to the page number 5, which gives you an obvious thing which can go wrong, and you should be very careful when you do reinterpretations. But it's very clear that you only should reinterpret measurements in terms of a BSM process if you have the same number of fiducial objects in the BSM case and the standard model case. So a very simple example is the Dralian process, set to mu, where you have 2 muons on particle and reconstruction level. And what you see now on the right side here are we compare the C factors for other background processes. So let's just go for the upper left column here. So therefore, the C factor for set to mu is something like 0.883. And this is very similar for TD bar, and it's also very similar for W plus, W minus, which is expected because, well, that's how physics is. However, once you go for a process where you have more, or where you can have more muons in the final state, then this starts to really deviate significantly. For example, WZ and ZZ. So this obviously is an obvious thing which you have to take care about. You must make sure that the number of final state objects is the same. So now the question is obviously, once you do this, how big are then the C factor model dependencies? Let's go for the next slide. We have just the idea how we actually model our detector. So there we just use a Delphis Atlas card. So we assume the Atlas detector in Delphis, and then went there through all the reconstructed signal samples which we have previously defined. And we also apply systematic uncertainties on the various objects, which are try to reassemble what we typically observe in the LHC experiments. Super important for these green interpretations are all observables which have a large tail. So for example, ET miss, where the truth distribution and the reconstruction distribution is significantly different. And actually this also differs for different processes. We'll come back to this point in a second. So let's go to the next slide, where actually we just look now for the different signal regions, which I already promised you. In total, we have 15 different selections for typical standard model and BSM processes. I don't want to go now to the full list. I just show you they are very broad, and we tried really to model very different aspects. So leptons, B-chats, chats, ETMS, all these things. Now we apply these signal selections on all our Monte Carlo samples, and then just look what comes out. And the results for the standard model case are actually shown on the next slide. So slide number 8. So what you see here now is for the left side, you see the muon results, the muon decay channel, and for the right side is the electron decay channel, just for be sure that things are consistent. And then you see different selections and different processes. Now, the typical C factors which you have in standard model processes are between 0.6 and 1, which is something essentially tells you that not too much migration effects happen. And now you just compare these C factors, you see that these C factors for typical standard model processes agree within 5 to 10%, not worse than 10%. Let's go one step further and go for BSM physics, which is shown on page number 9. So there you see EFT interpretation. So we modify the couplings in the standard model and then just check how big the effects here are. And so for most of the cases, we see also quite a good agreement between the C factors. However, there are some exceptions, in particular for the WZ and the WW case. And this actually just comes from the fact that you start to have migration effects here. That means when you have ET miss, then lots of your truth particles on the EFT scenario make it without migration effects to the fiducial volume. However, in the standard model, you have lots of migration effects. And actually, this leads to the differences of the C factors, but again, not more than 10%. And what we chose here are already very extreme scenarios. So let's go one step further for the BSM models like leptoquarks and SUSY on page number 10. Perfect. Thanks a lot. So you see here Z prime, TD bar, etc., etc. And then we just compare again. And again, we see here quite consistent results. There's a small difference for the leptoquarks, space, which is significant statistically, which actually comes again from the fact that you have detector resolution effects and migrations in and out. Okay, so this already brings me to one of the last slides, page number 11, where I summarize these studies. So, well, if you want to read the full thing, I pointed to this paper here. But if you want to do interpretations as a theoreticians, I think you can really do so as long as you make sure that the number of final state objects is the same and you're not really subjected to large migration effects. For all other cases, it's totally fine if you just apply a 5 to 10% uncertainty on your measurements and cite our paper that we said 5 to 10% is okay. And then you're completely fine to do this. So I think on page number 12 already, I come to the summary. So the basic idea of the study, I don't have to read now what's written there. The basic idea is seriously that we wanted to put an end to this discussion or to this argument, which always came, you can't do this because there's a model dependence. So obviously the answer is there is a model dependence. However, it's typically not more than 5 to 10% on the standard model process which you have. And that obviously allows you to place limits. It won't be the best limits ever, but will give you at least a first indication where you stand when you use these fiducial cross-section measurements to place limits on your model. And that brings me to the end of my talk.
Okay, thanks very much, Matthias, for the very interesting result here. Do you have questions? Check Mattermost. So how much of this result, this 5-10% result, depends on the generators being used?
Actually, we check it. We mainly used MATLAB and PCA8. We cross-checked with some other processes, but this completely stays stable. The main impact really comes from this. If you see differences which are more than 5%, this typically comes from the fact when you have very high cuts on ETMIS, where you have migration effects. So where your standard model process actually only makes it beyond your ETMIS cut simply due to migration, and not because there was a real true missing ET in your event. Yeah, so this is the main problem that you have, and it's completely independent from the generator.
That's very interesting. Yes. Okay. Any other questions? Okay, so hopefully theorist colleagues will be following your advice here. And thanks very much. Okay, our next speaker is Frederic Roux from University of Freiburg, and will be telling us about searching outside the box for supersymmetry with Atlas.
So, hello, yeah, after Matthias's nice talk, we'll just move back to direct searches for a bit. And searching outside the box, this time, this is not meant in the model space, but I'm more looking at the strategy of what we're doing regarding statistical analysis and how we define our searches. So, I mean, many of us just before the start of the LHC thought that, okay, there's probably some rich supersymmetry or other beyond the standard model phenomenology which will be uncovered. So we can just take our snorkeling set and then put it on, and then we can look at all these exotic things just below the surface. 10 years later, as you know, we really haven't found anything except for light Higgs boson yet. So if supersymmetry, for example, is implemented in nature at scales which we can probe, it's obviously difficult to find, else we would have seen something already. It's probably not your grandparents' M-Sukra or something like this, so it might have largely unknown characteristics and requires more and more sophisticated tools to basically search down here for a very different type of fish. And just on the next slide, what I'm talking about mostly is just on the very bottom, the search design and statistical tests. And this is just kind of to appreciate the work that everybody else put into us being able to do that. So of course we need the LHC and the Atlas detector, where they've went huge efforts and sophistication in to get the data to be able to dive that deep. And then in physics reconstruction and object reconstruction, there have been a lot of advancements in the last years, which are the instruments we use to look at these things. And then in the end, what we do is we design these searches and then look in the box. So a very simple SUSY search design is just you pick some discriminating variables, so some observables of physics objects or event level, where you have significant differences, hopefully in the distributions of signal and background, and then you pick some region. And I have this rough sketch on the right-hand side. Sometimes we do something we select on a resonance or something like this, but in many, many cases, what we do is we select on the tails of kinematic distributions. So that's what's pictured here in two arbitrary variables. So you have this background distribution, which just has this tail, so it just runs off in both of these variables. And then you have these blue expected signal events, and we just pick cuts in these 2 dimensions here to define a signal region or our box. And then inside this box defined by our cuts, we just count the number of events and data and check whether we have evidence for new physics. And this is a rather straightforward approach, just defining a simple box. And it actually has pretty good performance if you just optimize everything for a specific signal hypothesis. And one of the great things is also that it's very straightforward to reinterpret within and outside the experiment, because you just have this one number with an uncertainty, so you don't have to do anything sophisticated. If you have, if you have any expectation of how many signal models for your model would land in there, that's easy to do. And if we want to go beyond, the first question is, of course, I said, basically, this is pretty good for basically what you optimize for, so why should we go beyond cut and count? And as an example, I have the all-electronic stop search here, which you've seen earlier already, the results. And on the right-hand side, there's again it's a little picture how this simplified model phase space of the stop and the neutralino mass is split up. And you can see that there's specific signal regions defined as A, B, C, and so on to target specific areas in that region. And within kind of the really targeted area of one of these signal regions, for these hypotheses, really the sensitivity is really dominated by one of these bins. So it does not necessarily make sense to combine them in the region where they were designed for. But if you look at this exclusion plot, which you've similar seen before already also, then there's this blue area I highlighted, which is the kind of interplay or the handover between this SRA, the signal regions A and B. And what's done here is that there's actually a statistical combination. So that's a multi-bin fit or a multi-channel analysis over 6 channels, which are combined. And what does this do? The first thing is that you get, if you look to the left hand of the blue area, you see that all these different regions meet at acute angles, and you have these slices where we don't have coverage in between. And this is nicely filled out if you kind of do a statistical combination and a multi-bin fit. But that's not the main thing, actually, just in this simplified model context that you have a bit of an area which is excluded. But I mean, all these pictures are for simplified models. So you just have these 2 particles, all branching fractions are 100%. If you move beyond that, then really the whole area becomes important, and it's really important to combine these distinct regions in a multi-bin fit to get the best depths of coverage and also cover if you have low branching fractions and things like this for this scenario. There's different reasons to go for multi-bin analysis or multi-channel analysis, of course, and one example is the two-locked and stop search, which you've also seen already, and this just as an example, the 3-body region where you can see the picture of what's supposed to happen in the signal samples on the right-hand side. And what the case is here that you have events, the beat jets can be rather soft. So you have events, signal events distribute kind of over an area where you have beat jets recognized or you don't reconstruct any. And then you have same and different flavor combinations for the leptons. And signal goes over all these channels kind of a bit uniformly, but in the backgrounds are very, very different between these. So it makes a lot of sense to look at the backgrounds and try to constrain the backgrounds as good as possible in specific regions first, and then do a multi-channel analysis over these. And I just have these 2 pictures which show there's a variable which was used for the analysis in 2 of these kind of channels, just to show you that the colors are obviously different. So just to illustrate that, yes, background predictions are very different, and it's easier to tackle that individually and then combine these regions because signal lands in all of them. And the 2-body region and everything else in this analysis is likewise split. And this is not only to be sensitive to SUSY scenarios, but this also provides a lot of additional sensitivity to kind of related models, for example, dark matter production via scalar or pseudoscalar mediators as sketched in the bottom right. Okay. If you want to go beyond that, there's some cases where the really larger multidimensional grids are really varianted and something which you would like to do or which you need to do. And 2 examples here, the sketches of what signal events look like in a pseudo-Feynman diagram way on the right-hand side again. And 2 of these cases are Tracino-Trollino pair production or SUSY and ICHEP multiplicity events. And the problem here is that depending on the mass splitting of the SUSY particles involved there, you get very different event kinematics in different kind of regions in these simplified models of mass splittings. And you would like to cover all of them kind of to an equal extent without defining dozens of very specific optimized signal regions. And what's done is you pick some variables that you can select on, and then you create kind of this multi-dimensional grid where you do a maximum likelihood fit over. And you've seen the bottom left plot already before. And I just want to show you that this is kind of a 2-dimensional representation, but you can see with these statistics falling off several times, you can really see that this is more or less kind of slices of this multi-bin, multi-dimensional fit just being displayed in one line. In addition to doing this, we also always define single bin discovery signal regions to have a simple number for kind of the agreement of the standard model with the data. But what I would like to highlight more here is actually the differences between the single bin and the multi-bin fit. So if you use the single bin discovery regions for exclusion, then you've seen nearly exactly this figure, just with different lines before already. So this is from this analysis in the space of gluino mass and neutralino mass. And please don't look too much at the red line, which is the observed limit, but please focus on the dashed lines. And then you have one dashed line, which is the more innermost one. Basically, this is if you use a single bin statistical fit. And then you have the other one, which uses the multi-bin signal regions. What you can see is first at kind of high gluino mass, low neutralino mass, you see that there's actually not a big difference. So it's not, as I said earlier, it's not always much better to do a multi-bin fit, but if you really target a specific region, you can do as well this kind of single bin fit. But what you can also see is that just the multi-bin fit over the whole phase space we have here is just always better. So you provide a very uniform and very nice result over a lot of different kind of kinematic regions. Okay, so if you want to put more sophistication in, so if you might have seen that I have these small sketches on the top right of the slides that just show how schematically how these signal regions are built. And you might think you don't like these kind of horizontal and vertical lines or anything like this, but you would really like to have something which follows the signal very clearly, and you have the kind of more complicated shapes in the space spanned by your observables. And one thing, you can of course design new variables which kind of then represent non-orthogonal cuts in other more simple variables, but you can also say, okay, let's just have a neural network do that work for us. And this is an example from a stop production again, and in the sleep body region, just as the last stop result I showed you. And if you want to use machine learning to better classify events and kind of get something out where you can do a multi-bin analysis, then the problem you have here is that there's a lot of chats in the event. And if you don't construct the variables yourself, but you want a neural network to do that, you have to live with the fact that the number of inputs differs from event to event very widely. And this is why in this case, there was a chat-based recurrent neural network used, and the recurrent neural network just because it can best deal with this variable length input. And then the output of this neural network is fed to a shallow neural network, just one hidden layer, together with 12 other more conventional variables to get an estimator output, which you can see on the bottom left. And here you have a control region to constrain the background. This is a bin on the very left. Then you have a validation region to check whether that works. And then we do a shape fit basically in the rest. And if you look at this exclusion plot in the stop and the neutralino mass plane, then this analysis comes in the three body region and is this orange contour. And here you can see that while in all the other regions on this plot, there's usually different analysis or several analyses providing some coverage, you can really see that this analysis managed to go far beyond what all the others are doing, where you can see the merit of this approach. Okay.
You have 2 minutes left, Frederick.
Yeah, thanks. It's all nice and great, but you're not really interested in us excluding points in a simplified model phase space, I think. The typical Atlas SUSY publication is, of course, we publish first the results of the discovery phase, whether we found anything, and quantify the kind of agreement of the background with the data. And then we quantify the sensitivity using grids of simplified models. But the really critical thing is that we are able to apply these bounds to more complete and complex models. I mean, for measurements, Matthias nicely presented this already, and this is now more for the direct searches. What we want to do is really what we present is kind of this left-hand sketch on the top, which is just simplified model, which has two particles in there, very boring. What you want to have exclusions on full models where a lot more things happen. And this is very straightforward, as I said, for a simple cut and count region. But what about more complex fits? How can we actually allow people to use these to look at their models? And as I'm more focusing on the statistical approach in this talk, so the solution to that from the statistical side is called ICHEP. And you can see the web page here. And this is a pure Python implementation of the very common HISP factory PDF template. And we started basically this year or end of the last year, we started in Atlas for all the SUSY searches to publish our full likelihoods in this JSON format, which is used by ICHEP. And this really allows to rerun multi-bin or shape fits with identical inputs to the published result and including all the uncertainties and correlations. Now, the question is, of course, where do you get your signal predictions for our signal regions? And since the start of run 2 already, we are publishing these code snippets, which you can try to copy and paste into your code that have the event selection. Then, yeah, you usually need some kind of detector simulation, but that's covered and we provide a lot of information for validation. So just to show the proof of concept of this ICHEP, we published a public node. And what's done in this public node is that this one analysis is basically just used to go from a root HISP factory workspace to this ICHEP workspace and then back to this ICHEP workspace. And you can see the result on this plot. And there's different red lines and different dashed lines. No worries if you can't see them because they're perfectly on top of each other. And one nice thing, which is sketched here, this round trip for validation not only allows you to kind of validate what's happening, but it also allows you, if you like to root workspaces more, then you can just take our ICHEP workspaces and ask ICHEP to convert that to root workspaces. Okay, so as a summary and conclusion, we have a strong focus on searches for supersymmetry in Atlas, often using single bin search regions. Again, if you really optimize them for specific scenario, then they do very well. We don't have any evidence for physics beyond the standard model yet, so we are doing more and more multi-channel analysis and shape fits to try to dive deeper and find that magnificent beast on the right-hand side. And this not only allows us to go into corners of the phase space which are difficult to kind of tackle with single bin search region, but that also increases our sensitivity to related hypotheses like lepto quarks or dark matter production. Machine learning techniques are very widespread in Atlas and CMS already for kind of object tagging and reconstruction. And in Atlas, direct use by searches is becoming more common now. And I showed you one example. The challenge in all of this is, of course, to efficiently communicate the analysis setup, the inputs and the results for anyone outside of Atlas. And this challenge is overcome by the implementation and the use of ICHEP. And if you go to this ICHEP page I linked here, then there's a full list, at the moment still short, but growing by the week, basically, of all the livelihoods which are available. Thanks.
Thank you very much, Frederick. We have time for a couple of questions. Anyone?
It's Mia. Can you hear me?
Yes, go ahead, Mia.
How much of these new approach, machine learning above all, but these new approaches can be implemented at trigger level? Is Atlas thinking about doing analysis using trigger level object directly?
I mean, if you have trigger level objects saved offline, then you can use any of these things, of course. If you really wanted to do something online, it's technically possible, probably would end up with you using large lookup tables or something to not. I mean, the problem is always there's a lot of tools to deal with multivariate analysis and neural networks. Everybody has his own preferences. So kind of getting this under one umbrella to use this efficiently across the experiment is a bit of a challenge, which we're working on. But I mean, it's definitely possible.
I had a somewhat related question, more on the offline side, with this more, complex fits that you are doing here with multi-channel analysis and shape fits. Do you need to take into account needing more resources, more computational resources, like high performance computing type of resources, or what currently exists is enough?
I mean, from computing resources wise and so on, if you would, I mean, if you download, for example, the ICHEP template for the analysis, which is shown here, and then you run a complex multi-bin fit, this is basically running within seconds. So even if you want to run over, I mean, which we'll also do internally, even if you want to run over 1 or 2 million different models, that's technically feasible, and there's no limitation, I think. I mean, yes, it will take a few weeks, but there's no kind of nothing stopping you from doing that. This is one of the big advantages of using ICHEP over this root hystractio templates, that it's just so much faster.
Excellent. That's great to hear. Okay, if there are no further questions, thank you again. And we're going to continue on this vein with the next talk, which is by Miguel Crispin Romão from Lisbon on deep learning versatility in new physics searches.
Yes, hello. Let me just find the window, which is this one. And okay, so I will assume everything is fine, right?
Looks fine, yeah.
Okay, thank you very much for the opportunity of giving the talk. I'm going to be talking about some of our current work on deep learning, and it's easier just to do the physics searches, but in specific to help us to do more generic searches that do not rely on signal assumptions. So one of the main goals of the LHC, as you know, is to look for BSM. And what you normally do is that you choose the signal that you are interested in. You study what's the favorable kinematic and the final state topologies. You collect data in that regime. You apply cuts and etc. And eventually you perform statistical tests on the data with the hypothesis of the BSM being present or not. And then eventually, hopefully, at some point during the LHC lifetime, we will profit. So we started doing some exploratory work last year, and then we eventually published this year on how could you use neural networks to find certain types of signals, and how would they transfer once you train on a specific signal on detecting a novel signal that was not using training. So this is a paper that's it's presented here. So the idea is you train a neural network classifier, just like Frederick was doing before, to isolate a signal against the background, and then you would like to do some, you'd like to see how it would perform if the signal present in the data was different from the one trained. So we have three classes of signals that we use: an FCNC signal associated with the Z production, and then we have VLQ with actually top partners only, so VLTs, produced through standard model gluons, so pre-production, and then we also had with a heavy gluon, which can come from, for example, composited Higgs models. For the VLQ cases, we considered three different points in the mass for the VLTs. So our initial idea was to see how sensitivity would change as you would go along the mass, for example, and then we decided to complicate a bit more by adding a heavy gluon, which will produce a very boosted regime. So we have a different kinematic regime with similar final state. And then we put an extreme case, an edge case, which would be the FCNC, which has kinematics and final state, which are very similar to the standard model. So the analogy here is you train a neural network to detect a specific monkey or specific type of animal against the background of the jungle. And then what happens if your animal is actually not a monkey, but it's like a pink panther, or etc. With your neural network, your discriminant will be able to pick it up. So for each one of these signals, we trained a supervised classifier. So that specific signal against the background. We use the same background for all of them to make a fair comparison. And then we assess the discrimination, how the discrimination deteriorates if you change the signal that's present in the data. And we computed expected upper limits on the cross-section of each of the signals. So from a machine learning metrics point of view, you can see that there is the neural networks do retain a discriminative power as you change from the signal that was trained. So these two left-hand plots are for the model that was trained on a vector-like T that was produced by the standard model gluon, so without a heavy gluon, at a mass of 1.4 TeVs. And you see that the area under the rock, which is a very common machine learning metric, is very good for all the signals which have VLTs in the final state, but you still have some discriminative power to detect FCNC. This is quite a bit surprising, considering the FCNC is very similar to the standard model. It does not have a heavy final state, does not have a boosted kinematic, so it's quite different. So for example, here you can see how finding the FCNC, so in a dedicated model, so the supervised model, to find the specific FCNC model, you have a fairly good ROC, a 95%, which is acceptable. But all the other models that were trained on VL quarks, VLTs, with or without a heavy gluon, were still able to retain some discriminative power. So this was a bit of a surprising result for us. This is what motivated us to go forward with this. And then we performed upper limits on the expected cross-section. So in order to understand this, I think that the right-hand heat map is the best one to understand what we're trying to, the message we're trying to convey here. So the diagonal would have are the values of the μs for the dedicated, so for the supervised classifier. And as you go along the lines, you'll be using a discriminant was used with another signal. So you would see like how the supervised classifier deteriorates as you go along other discriminants that were trained with other signals. So what's very interesting here is that the FCNC, your limits on this specific FCNC signal deteriorate at most an order of magnitude when you have a neural network trained on vector-like quarks, which we're quite surprised about that result. More interestingly is that if you train a neural network on the FCNC signal, you actually still retain quite good sensitivity for all the vector-like quarks with discrimination degrading less than an order of magnitude. I have to say that there are error bars here, which are not present, but they are in the paper. So that's important to talk about this lower left square here, where we see that all of these numbers are actually compatible with 1, which means that regardless of which vector-like quark signal you trained on, you basically maintain exactly the same sensitivity when deriving upper limits. Importantly to know is that this is also true when you go from a heavy gluon regime, which you're going to have really heavy boosted objects, to a standard model regime where this is mitigated. Okay, so this is all fun and games, and we published that, but couldn't we just focus on learning about the jungle and hopefully be able to identify any animal that would come across when we're looking for something? So the idea here would be to have something that learns about the standard model quite well and would be able to identify outliers or anomalies that would be then candidates for BSM physics. So there is a growing interest in unsupervised methods exactly for this, because you don't have to assume a specific signal for your analysis. So for this, one of the more important ones is the broad range of models called anomaly detection algorithms. So basically this will try to learn what would be a normal or a regular event, and then we'll try to assign anomaly score for things which are less likely to be part of that distribution. And then we could then in principle use that anomaly score as a discriminant for new physics. So I will also recommend CERN's International Machine Learning Workgroup. They have an ongoing and live review of all the machine learning applications in high energy physics. So it's a really nice place to go to if you want to start learning about a specific application. So this is a paper that we have out and it's now in a process of peer reviewing. So we kept the same signals and we kept the same backgrounds. What we did was we compared 4 different anomaly detection algorithms and derived limits on the discriminant provided by the anomaly score derived from each one of these algorithms. Since I don't have enough time, I won't be able to present the isolation force and histogram based one, which are not deep learning based, are not neural network based. I will focus on the 2 deep learning based ones, which is the autoencoder and the DeepSVDD. If there are questions, I have them in the background slides. So what is an autoencoder? An autoencoder is, as the name says, it's a network that learns how to encode data into a lower dimensional space and then tries to reconstruct it. And the better it reconstructs, it means the better it was able to learn all the meaningful features to embed the data into this lower dimensional space. So the idea is that this, what we call the latent layer, has a dimensionality loss smaller than the input space. And then the neural network will have to learn all the meaningful features in order to embed in this lower dimensional space and then be able to properly reconstruct. In that sense, how well you reconstruct, which is basically the mean square error of the input versus the output of the autoencoder, is a measurement of how well the neural network learn how to reconstruct that type of event. And so in principle, the idea would be that events which are harder to reconstruct once the neural network is trained are more likely to be BSM events because they would have been less like the standard model events that the neural network had to learn to reconstruct. And then we developed this DeepSVDD. SVDD stands for support vector data discrimination. And the idea is quite different. So here the idea is that you use the neural network to embed your input variables, your events into a lower dimensional space. But then what you do with this embedding is different. So what you do is in this embedding space, you can derive what's the center of mass, which is basically the weighted average of your sample. So it will give you like the mode of your distribution in this embedding space. And then what you do is you try to compress the sample into this point. So you try to reduce the average distance of the points to the center of mass. And this actually has a very nice statistical interpretation where this distance to this center actually is related to the quantiles of likelihood of a point having been sampled from the statistical distribution where this was trained. So that it has a very nice statistical interpretation of the further you are from the center of mass C, the least likely it is for that point to have been sampled from the distribution where the DeepSVDD was trained.
Yeah, you have 2 minutes left.
The main point here is that you only train on standard model, okay, and then you pass different BSM candidates and derive limits on it to see how does it go. So the first thing that we've learned is that they actually do not learn the same thing. So you can see here for the autoencoder and DeepSVDD output on standard model samples that they are not correlated. So the autoencoder and the DeepSVDD are learning different aspects of the data. And it can indeed isolate signal to a certain extent. So you see that the distribution of the anomaly score for the background and for different BSM candidates is different, okay? So In normal, the BSM candidate has shifted to the right, so you'll have a discriminative power to try to differentiate between any type of signal from background. You can then produce limits. Again, we compared against a supervised DNN. Obviously, the supervised discriminant will be better in principle because it learned that very specific signal. But you can see that, for example, for the autoencoder for very boosted and different objects like the VL keys, you don't lose much sensitivity on driving your limits, whereas the deep SVD seems to have a more of a uniform performance across the board with around an order of magnitude degradation. But this is incredible because you only train on standard models, so you're able to derive limits on any type of BSM physics present in the data. So concluding, neural networks provide a very versatile solution for generic searches. So not only support supervised neural network classifiers can also identify other signals that were not used during training, but unsupervised methods seem to provide an even more satisfying approach to the problem, which is you only learn about the standard model and you still you get a new variable which has discriminative power against any BSM model. So there's still a lot of work to be done. So that we want to extend this to different kinematic and topological regimes because all of these samples and signals and standard model were in a D-leptonic regime. So we want to extend to other cases. So this will also mean that we want to diversify to other BSM candidates in other kinematical and topological regimes. And you also want to start using more unsupervised statistical tests because those limits are using the CLS method. So it means that you still have to develop a notion of expected signal versus expected background to drive those limits. But there is some effort in the community into trying to get a uniformized unsupervised statistical tests on the presence of BSM on a certain sample using these methods. Thank you.
Okay. Thanks very much, Miguel. We do have time for questions, so let's open for that. Any questions? From the audience. So I had one regarding the way you build your deep neural network. You're taking into account the reconstruction of your signal and backgrounds when you're training, right? So the quality of the reconstruction will influence to some extent the quality of your output.
Yes, exactly. That's a very good question. So we are using, so maybe I should have been more clear about that, but I don't have that much time in 15 minutes.
Well, you now have some time.
Yes. So we are using high-level variables of reconstructed objects. So basically, we are using what Delphs gives us. So our pipeline is MADGraph, Pythia, and Delphs, and with the default CMS card. And so we have those variables, right? In principle, yes, you say that there are systematics on the reconstruction, and so this will be imprinted in this method. So one of the other areas of work that we are now planning, which I should have put in that bullet point, is how to make these things more robust against and systematics like those, for example, so that we would be a little bit more comfortable when understanding that reconstruction has its own errors and etc. Yeah.
Do you envision a future where you could even bypass reconstruction and reconstruct event images? We're trying to do that in neutrino physics. So.
That's very interesting. So if you guys read the abstract of this talk, I was going to talk about another work that we've published, but it had to be cut out, where we use this thing called Earth moving distances, where you use exactly colorimeter and ID images. So you have like the colorimeter image of events, and you basically try to find out how different they are across samples, and we have been able to cluster them. And we want to also use that in the future to be able to identify anomalies. So yes, there is work in that direction.
Well, very good. I'll look at that if it's in your abstract, or maybe you can post on Mattermost if you have any paper on that.
Okay, brilliant. Thank you very much then.
Thanks. Yeah, thank you. Any questions before we move on to the next speaker? All right, if not, then thanks again. All right, let's move on to the next talk, who is going to be delivered by Xian Chen. Yes, Xian Chen from University of Pennsylvania, and is going to tell us about reconstruction techniques in Atlas.
I heard anybody else try to say something. Am I okay to start with already?
I think you're good to go, yes.
Okay. All right, so let me just share this first full screen. Okay, so this talk is about the reconstruction techniques for some category of atlas analysis in SUSY using the soft objects in the final state. So let me start with some introduction. So we want to use this soft objects first of all. So these analyses are targeting so-called the compressed regime in the SUSY. And this is a very generic feature, particularly when you talk about the LSP, the lightest SUSY particle, and the next lightest SUSY particle compressed. And this is, for example, typically motivated by SUSY dark matters, many SUSY dark matter scenarios. For example, if you assume R parity and conservation and with neutralino LSPs, which is kind of always the assumption for the wind SUSY. So this, immediately you will have a pattern of these compressed mass spectrum. For instance, if you have Wino or Higgsino as the LSP, these compressed chargino neutrino is a built-in feature. So for example, you have very compressed 160 MeV for the pure Wino LSP case, or you can have a slightly larger mass splitting if you for the Higgsino LSP scenarios, and also the Higgsino triplet is very sensitive to the other SUSY masses, so this can be a little bit larger still, like up to like a few GeV. The Beano LSP case is a little bit non-trivial, but you still need pretty much the LSP closely mass in order to avoid these overabundance in the dark matter Higgs density. And for instance, you can have a Wino or Higgsino or stop everything basically to mix or co-annihilate it to get larger annihilation cross section to get them avoid the limit from the measurement or observation. And you also have the good motivation to directly look at these as opposed to the other analysis where you assume much heavier masses to be produced. And, because, that's a non-trivial assumption. And if your assumption is wrong, then this is a unique probe to those scenarios. And okay, so then how we look at those. So first of all, we need a hard RSR associated with these productions. And this is to trigger the event by using the large associated missing ET. And this is like a monojet analysis. And this is one of very general analysis. But this is too broad, so it has a ton of background at this point. So we need additional handle to reject those backgrounds. And the soft object is something you can still try to look at. For instance, in a very compressed case, we have like soft pion. And if you have slightly larger mass pulling from Higgsino, for example, you can have still like a soft hadrons or leptons. And in case you have stop production and stuff like that, you can also have soft B-jets to be reconstructed. And and this is very hard, very painful, as you can imagine, because we are the Hadron Collider experiment with 50 pilots. But if this is the only way to go, we have to go. And and typically, this soft object reconstruction is limited by either the low acceptance due to the the PT threshold for the reconstruction, because you can imagine this lowest PT, the PT threshold is almost roughly correspond to the delta M mass splitting we can reach. And also there are tons of more fake backgrounds because of your low PT. So the pursuit is pretty much, quest the lowest possible PT threshold and keep the background rate, background rejection relatively reasonable still. And they're gonna talk about maybe three things that happened, the progress happened in these years. So one is soft lepton tagging for general compressed spectral search, and also the soft B tagging, especially for the stop compressed with the electroweak Kino case, and the soft pions for the long-lived pure Wino Higgsino analysis. And here you can, just to let you have a sense that, where is the so-called compressed parameter space. And here are the areas we want to target with using these new techniques. Okay, so starting with the soft lepton. So currently Atlas use 4.5 GeV electrons and also 3 GeV muons. And the electron performance is based on benefit by so-called supercluster reconstruction, which is the baseline since 3 years ago, I guess, in Atlas. And this is the clustering method that also take care not only the color cluster in the detector, but also some straight Bremsstrahlung small clusters into account. And this is very beneficial for reconstructing, particularly the low PT clusters, electron clusters. So you can see on the left top, the efficiency is at this lowest 1.5 GeV, you can still have like a 17% efficiency. And after the reconstruction, we also have the ID process called ID to reject further backgrounds. And at this low PT, we also maintain like a 75% to reject those backgrounds. Means beside these standard reconstructions, we also have a so-called low PT working point to specifically target the super low 3 GeV muons. And this is because in the standard reconstruction, we have a kind of inefficiency in the barrel because of, muon has to penetrate for 3 GeV muon, it penetrate, the efficiency for penetrating the outside most detector is not very much trivial. So they had a fine-tuned review of the selection, and they could maintain 90% efficient across the board with using this low PT working point with still reasonable level of background increase here. You can see on the right top. And then after this reconstruction ID, we also have a step called isolation to further reject the fake lepton backgrounds, including some of the kind of real leptons from the B or C heavy flavor hadron decays, where typically, they draft a little bit more than the usual leptons from hard collision. So we call this non-prompt leptons. And usually we just require the isolation, less activity in terms of track or calculations around the lepton candidate, but there's also a dedicated, more sophisticated algorithm using BDT, for instance. Here we have so-called non-prompt BDT, which is the initially developed in the Higgs analysis, but recently there is a retune developed by the SUDI analysis targeting more lower PT, this analysis is the electroweak 3 electron analysis. I think Sarah discussed in this session earlier. And this actually bring huge improvements in the sensitivity. And specifically, the fake can be reduced further after this isolation by factor 4 with still like a 90% efficiency by the BDT. And even lower PT, there's also some aggressive attempt to look in even below the lepton reconstruction threshold, which is the 4.5 electron and 3 GeV for the muons. And this is because the bottleneck for those reconstruction is either in the calorimeter or in the muon detector. So by looking just at the innermost part of the detector, we can still avoid this bottleneck. And the idea is to just look at the inner tracker track and with specific dedicated isolation applies. And for instance, this is done by one of our Higgsino analysis. So one item called the isolated track on the left top is the stuff. And here you can see the efficiency is pretty good down to like a 2 GeV. And this also drives the unique sensitivity to the smallest mass splitting for the Higgsino triplet on the right, you can see. So the expect limit is in dotted below dotted line here. So you can see that this actually adds slightly slightly in the plot, but this is actually a good improvement. So those are the highlights from the soft lepton case side, and I start talking about the soft lepton, so B tagging here now. So the bottleneck for reconstructing the low PT B tagging in Atlas, at least so far, is that the low PT B hadron doesn't really look like a jet anymore. Because you can imagine the 5 GeV, for example, initial B quark won't allow your decay object to collimate too much. And so it's not like a jet, but rather like a sprayed tracks or stuff like that. So you can, for instance, the gray arrows on the right left top is kind of a schematic. So a new development is to then just look at the secondary vertex structure, which is the most prominent feature for the B tagging. And instead of forming the jet and do the B tagging after that or something like that. And so they take a multi-display tracks as a seed for the secondary vertex reconstruction. And after that, still some optimized selection applied on those SV secondary vertex features to reject the high background in low PT. And this the performances, for example, on the left top here. So those dots are some of the working points using this new secondary vertex only B tagging, and the line overlays are the rock curves from the CaloJet based B tagging, which is the standard one, or the track jet based. You can see still, this new working points overperform pretty much. And we also checked the modeling, MC modeling user data, which is kind of okay. And this also drastically contributes to the improves massively the compressed sensitivity to the sum of the stop models.
You have 2 minutes left here.
Yeah, thank you. Okay, so last one is about the soft pi tagging in the disappearing track analysis. So first of all, this is targeting the pure Wiener or hexeno compressed triplet or doublet. And the biggest feature, first of all, is these particles are long-lived enough so that they can actually penetrate the detector, interact with the detector directly. And for instance, on the top, you can see that the Chargino in the red just pass through the innermost pixel detector and decay half through, and emitting just LSP as a missing particle, and also associated soft pi, which is like 100 MeV or so. And the pursuit, new pursuit we have now is actually not only just look at the disappearing track that we have been doing for already a long time, but also try to reconstruct the associated pi to further have a handle to reject the background. And this is done in a little bit fine-tuned way because this is a soft track, and there are tons of soft track in the events. So the ROI, region of interest, is limited into the cone of point A around this soft, in this tracklet, which is disappearing track here. And after doing that, take the endpoint of the tracklet at the origin and run the standard tracking. This achieved actually a pretty good efficiency of finding a pi track here, which is down to like 200 MeV. And then what it do after all is to try to associate those track candidates to the tracklet by forming the secondary vertex again. And this is also working pretty well. So the finding efficiency is like 90%. And the challenge now is basically for one, this pi and track plus this secondary vertex, you have still like 10 times more combinatorial backgrounds, and the background rejection algorithm is still being developed. And this is a pretty interesting and challenging task to move forward. All right, so this bring me to the conclusion. So the soft object reconstruction is the key component for these compressed spectral analysis searches for SUSY, and the lowest possible PT and the efficient strong fake rejection is our pursuit. And the recent achievements is summarized here. So the 3 GB for down to 3 GB, soft leptin down to 3 GB, and the track-based soft track tagging down to 1 GB, and the soft B tagging down to 5 GB, and lastly the soft pi tagging down to 12 MeV. And there are already a few analyses that actually apply these new techniques, but we expect more to come now. So just stay tuned for the new results to come. All right, that's it. Thanks so much.
Thank you very much, Fion, for this very interesting new techniques. We have time for questions.
It's Mia. I have a strong bias on the tracking because I'm the tracking convener in CMS. So I'm sorry for that. I will concentrate on that part. So regarding this soft Pion, from the last Connecting the Dots 2020, I learned that the new development were targeting such low PT phase space for run 3. While in this presentation, I understand that you are going to apply it rerunning the tracking on run 2 dataset as well?
That's a good question. So in principle, we can do that, but I'm not sure about the time scale, about the plan. So we have a dedicated stream called the D row, which actually can allow, which actually reconstructs using the hits, but with much less number of events. So so in principle, we can do before even run 3. However, I think I'm not actually the analysis the person doing this. So yeah, it might take still long, depend on many factors.
Sure. And then another question, I'm sorry. In slide 10, you mentioned PT order of 100 MeV. Then you always write 200. I understand that order, but it makes a very big difference, I guess.
Sorry, this might be confusing, yeah. So I should say, yeah, from 200 MeV in that case, yeah.
So the target is starting at 200, or you are trying to go even down, lower?
Yeah, so I think most of the signal events still has higher and less than 200 MeV if you're talking about like we know. So I think, you know, if they could do, I think, you know, still, yeah, even lower PT is still the scope.
Okay. Any other questions? Very good. Thanks again, Xian. And that brings us to the last talk of this session, but not least, of course, by Darius Farouhi from University of Zurich on uncovering hidden new physics using Bayesian probabilistic models.
Hello, can you hear me?
Yes. Can you share your slides?
Yes. Give me a second. Mm-hmm. Can you see them?
Yep.
Okay.
Very good.
Okay, I want to thank the organizers for the opportunity to for me to present some of the work that I've been doing for the last couple of years about uncovering hidden new physics patterns in collider events, and it's based on these two papers that kind of recent two papers that we've written. So in the last couple of years, there has been some progress in trying to come up with ways to search for new physics without any supervision. And here's a list of some of these methods. But what's clear is that unsupervised LHC searches are quite challenging. And to push these efforts even further, we actually need to gain a deeper understanding of what collision events are. And it seems that, I'm saying this because it seems that collider events are much richer than what we would have expected them to be. And a nice example of that is like, for example, you can equip the space of collider events with a metric, and you can use this to compute stuff, which is very interesting. In this talk, I actually wish to highlight other interesting things that you can do with events. So, for example, you can ask some very simple questions like, is it possible to write down a simple statistical model for generic collider events? And if yes, can you use this for an unsupervised classification of events? And surprisingly, it's actually not very difficult to do this. And this is something we worked in these papers. And it's just based on very simple statistics, and specifically on Bayesian probabilistic generative modeling. So this is what I wish to show in this talk. So to start, the first thing you need to do is to ask the question, what is a collider event? And the most general, maybe one of the most general ways of representing collider events is to just imagine they're a sequence of multiple measurements. So so these measurements, what I call here a small o, they take values in some phase space of which is spanned by some set of observables that you can decide what they are. They can be high level or low level observables. It doesn't matter. But so in this picture, events are just stochastic point processes in phase space. So having this very general setting, how can we actually model the joint probability distribution of what an event is? And it turns out that, at least what we found out, is that you can, under three very broad assumptions, you can do this. And so the first one is an exchangeability of measurements. The second one is to discretize phase space. And the third one is to assume that there's some multiple latent categories contributed to event generation. Yeah, so that's what I'm going to explain in the next 3 slides. But before, a disclaimer. So when our task is actually to classify events, not to build a faithful event generator. So that's just for you to understand. Okay, so the first assumption is exchangeability. So what does this mean? It's very simple. It's just that the order in which measurements within an event are sampled is irrelevant. So you have like this permutation group, permutation symmetry. And there's a very nice theorem that tells us that if measurements are exchangeable, that then the joint distribution has to have this form here. So it's an integral representation. And so what this means is that there has to be some variable omega, small omega, living in some latent space. So these are hidden variables. And then there has to be a prior over this latent space. And then you have something that looks like a likelihood. So it kind of motivates a bit Bayesian setting. And this is an existence theorem. So it's very nice that from a symmetry, you get some constraint on what are the possible models. But of course, okay, exchangeability is an assumption. So obviously we get this from that. And what this tells us is that measurements are actually considered conditionally independent. So they're not completely independent, but they're actually conditionally dependent on this latent variable, which has been marginalized. Sorry. So what the theorem doesn't tell us is what are these priors and likelihoods. So what are what are these? And for that you need some extra model building. And that takes us to the second assumption, which is phase space discretization. So this is very simple. You just bin the measurements. So you bin the phase space where the observables live. And this binning naturally leads to multinomial distributions, which are just a generalization of the binomial distribution, which is used for coin flipping experiments, right? So these multinomial distributions are the same thing, but for dice. No? So rolling a dice of m sides, where m is the number of bins in your observable in your phase space, and this is parameterized by this vector beta, which is just some parameters, and they're actually the probabilities, no, of landing for an event landing in the mth bin, for example. And so sampling, so measurements are just simply generated by rolling a dice in this picture, which is quite simple. And so since we want to have a Bayesian setting, you have to actually put priors on everything. So these betas, which live in a simplex, you have to put a prior over them. And the simplest prior that is non-trivial that you can use is the Dirichlet distribution, which is what I have here. This distribution is parameterized by this concentration parameter alpha. And it's a very versatile family of distributions. So for different alphas, you get actually very different shapes of the densities over the simplex. So here's an example where you have a 2 simplex. So it's, yeah. And the nice thing is that the Dirichlet is conjugate to the multinomial. So the posterior that you would get is actually also Dirichlet. So the third assumption is that we have to assume, so we assume that the data is generated from not one, but several multinomials over this phase space. And these multinomials, we call them themes or topics. And this is a terminology that comes from natural language processing. So this is where these distributions are used a lot there. And so so yeah. So these multinomials are now going to be parameterized with an extra index t, which tells you which theme you have besides the so the number of parameters in the model is just t times m, where t is the number of themes, so this is capital T, and capital M is the number of bins. And so these themes is where all the physics is. So each theme encodes a different information about the hidden structure that's in the collider. So to each theme, there should be associated at least some physical process or some phenomena that's underlying in the data. In most of our work, we actually use the T = 2, so only 2 themes. We'll see later in, when I show an application. So because it's easier, and also you want to actually distinguish beyond the standard model from the standard model, so you just need 2 themes for that. So now with these assumptions, now we're ready to introduce the model that we found the most interesting one. So here's the full model. It's called latent Dirichlet allocation. And this is just a mixed membership model. By this, I mean that events are described by mixtures of multiple latent multinomial distributions. That means themes, which are here. And then there's the latent variable is this, are the mixing proportions of these themes. And this is where so this is integrated over Dirichlet where these mixing proportions live. And the prior is obviously a Dirichlet, as I mentioned before. So here are all the ingredients. So it's important to stress that these individual events are described by a mixture of distributions. So maybe it's easier to show a generative process. So how does the generative process go? So in this example here, I have just 3 themes. And what you do is you first sample from the simplex 1 point. And then with this, given this theme mix in proportions, you then sample a theme, which here happens to be the second one, the blue one. And then from here, so since these are multinomials, then you can roll a dice and you get the bin, you get some bin. And you just repeat this for all the measurements in the event. And you do this several times until you exhaust all the measurements in the event. So then your event has this, is going to be just a mixture of 3 different themes. And then you do this for all the events. So you just sample from the Dirichlet randomly, and you get your data sample. So this is how the events are generated in this model. And it's important to stress that mixed membership models are really not to be confused with mixture models. So the former allows for shared features between events, so they're more flexible. But the mixture models actually are much more rigid. So, and if a single event will come from just 1 theme. So so this is a very big difference.
You have 2 minutes left. Sorry.
2 minutes. So, so now I'm going to talk about, so the inference is quite direct. You just want to solve using, you want to solve the posterior to get the parameters of the multinomials of the themes and the mixing proportions. And you do this using variational inference. And so the question is, what does the LDA actually learn? So it just learns co-occurrence of measurement bins and events. And then, so what you can do is write down a likelihood ratio of the 2 themes, and you can compute it for every event and just, pick a threshold, and then you can classify events using this. So you can use this for uncovering hidden patterns inside jets, and this is what we did in our paper. So the data representation is just the binary tree, so what we do is a jet declustering history. We extract, we first cluster all the jets in a dijet sample using a fat jet, using a R = 1. And then we uncluster each of the jets and extract at each splitting some observables. So the observables we use are actually these 2 here. So we use either the mass basis, which uses the soft drop and the invariant mass, or some other, we have here the Loon basis, which are these observables here, the KT measure distance and the inverse of the separation. And these are good for discriminating between QCD and the heavy resonances. So those were the observables we used. And so we trained a 2-theme LDA model on unlabeled dijet samples with QCD and a signal. And the 2 signals we used was, so first the typical boosted top scenario, which is a standard candle for this type of analysis. And then we also had something a bit more complicated, which is this cascade decays with a 3T VW prime and some scalar that decays to W's. So we tuned our Dirichlet prior for it to be very asymmetric. So this way the themes can actually align with, for example, QCD. One theme is going to be mostly QCD, and the other theme would actually pick up something rare in the events. Hopefully, of course, BSM. So these are the results. Well, these are not the results, but these are so this is the sample we use, for example, for the top quark. This is the phase space. So this is the mixed training sample. So it has 5% and 50,000 events. And so the truth level distributions are here on the right. For QCD, you see it has a nicely falling distribution, while for the top, you expect these features here that have to do with the mass of the top and the W. So what LDA uncovered was this. So you can see it's actually it really discovered the top, which is very interesting. And for the BSM search, it's, okay, here I'm showing the other set of observables, which is the Lund plane. Again, it's the same story. In this case, the signal has these features also which represent also the massive decays, like of the phi here and the W for each of the leading and subleading jets. So what LDA uncovered was actually this, also the same. So it really discovered the signal in this case, and also even some of the deficits that you have, some other features which are at low in the non-perturbative regime, which is also interesting. So, okay, conclusion. So we showed that it is possible to model collider events with a simple probability distribution that is capable of capturing hidden structures in the data. And this can be used for classification tasks. The method is based on Bayesian probabilistic modeling using 3 broad assumptions, which is exchangeability of measurements. Probability distributions are assumed to be multinomials with Dirichlet priors. And you assume that there are multiple categories of these, so several of these multinomials. Then we focus on one collider model, which is the latent Dirichlet allocation. So here, the events are mixtures of latent themes. It's a mixed membership model. And what's interesting is that this is just one option. You can actually, there's probably much more, so you can do much more than this. So this is just one example. You can do, so this opens it paves the way for model building for data, which maybe could be interesting to explore some other possibilities. Okay, I gave an example where we used the 2-theme LDA to show that it actually can find the top quark and some BSM decay cascade and digest events. Thank you.
Thank you very much, Darius. We have time for an urgent question. See anyone? This looks very promising.
Yeah.
From just 50K training event to discover the top. So that's,
well, it's no, okay. I mean, this was a 5% signal over background ratio.
Sure.
So it's, but still, yes, it's quite promising, especially if the new physics is it's like a complex. That's what's more promising.
All right, if there are no further questions, I guess we're in lunchtime now, but the session is going to continue, going to stay open until 2 o'clock. So feel free to stay around and discuss it, if you have questions that have arisen between the talks and now. But we're going to conclude the session here. So thank you to all the speakers for their excellent talks, not just today, but also during the week for making this and all the discussion for making these very exciting sessions. And I hope you all keep enjoying ICHEP 2020, which of course continues through the next week. So thank you, everyone.